Please tell me you hear my microphone. Please tell me, please tell me. I think I see, it looks like it's lighting up. Please tell me you hear my microphone. This has been nuts today. Yes? Everything's crossed. I'm not seeing anyone. Yahoo, we are live with sound. Oh. The beads of sweat are dripping. No. I think I had a hardware failure, which is yay with sound, everybody. Oh, good, good, good. I think I had a hardware failure. I use I will plug this not because it failed, but because they usually are so good. I use these little guys. Whoop, as I drop it, I use these little guys. They're typically very robust, really good little things. They can basically solve bunches of problems, and they're portable, so I'm able to take them all around to different computers. And instead of installing a card in my actual computer that then is locked into that PC, obviously, I can use this anywhere, right? I can use this on anything, and they're 4K, at least the new ones are. And they're really, they've just saved my life. But I think I had one fail. And that makes sense because I'm online so often, right? So I think I have a dead one, and we'll see. I'll have to do more troubleshooting later. But luckily, restarting the system, kind of moving things around, and shuffling stuff around. I also think YouTube is doing some weird stuff because they just keep changing their interface, so that makes things tougher. But nonetheless, we've got sound, we're good, and that makes me extremely happy because what I was saying before, when you guys couldn't hear me, was that I spent something like 5 hours over the past week putting together some material in this particular course that I haven't even taught to my Millersville students yet. And the reason why was because I kept getting people asking me questions about power grids. I think most people believe that the power grids are basically things that can just be shut down in the case of inclement space weather. Just shut them down, and everything will be fine. No, that's not right. That's actually worse. And people go, well, why? I don't understand. And I say, well, it has something to do with reactive power. And they're like, what's that? I have no idea what that is. So it became clear that I really need to try to do my best to explain reactive power at the 50-foot, the 50,000-foot level, right? Kind of like peering down on it from a very simplistic point of view, because it's very easy to get into the minutiae and get into the weeds, and definitely easy to get into stuff that I don't even understand, because I just have never been skilled in that area. I'm not trained in that area. So I'm going to try to give you that 50,000-foot level view with what we're going to talk about today. And I'm actually quite excited because it's really interesting stuff. And hopefully we'll see if I can teach it. And if there's any electrical engineers in the house, please forgive me. Because, again, this is not my bailiwick. There's certain aspects, obviously, that are, but there are certain aspects that aren't. And so I'm going to talk about some of the people who have really been working hard on this stuff, and hopefully highlighting a little bit of their work, because it's a really incredibly difficult problem, and we'll start understanding the size and the scale of that. But at first, I just want to say hello to everyone. Thank you so much for hanging in there with me. This has been an adventure this morning, hasn't it? So hi to all of you. I hope those of you who are in, over the pond, it isn't too late. I tried to get this one to happen a little bit earlier, but obviously the technical issues caused me problems and slowed us down. So thank you for the troopers that you are staying with me. We are now in the third part of basically the ground level effects, right? So we have started way back when. We started with the sun, and we did all the phenomenology with the sun to about basically the Earth, and we called that the first chef. And that basically is all the solar phenomena that lots of people play with and hear about and are petrified by. But that is only part of the story, right? Once we get to the near Earth environment, then we have the second chef. It takes over, and it takes those eggs and cracks them into a skillet and scrambles them up and turns those solar phenomena into things that you would hardly recognize, right? And those things then propagate down in the Earth's magnetic system, down through the Earth's, what we call the Earth's magnetosphere, down into the upper atmosphere, which we call the ionosphere, and then through that, and then down finally to the ground. And that's where we are now. If you are a Patreon member, you have all of the something like 28 or 29 courses now that have been cataloged for you. And I will likely, because I've gotten a lot of good feedback from my behind the scenes group, my Rocket to My World group, they've told me that they really love how that is all structured. So I will likely release that to the rest of my Patreon family so you guys can really see, if you're wanting to go through the entire course list all the way through, to be able to kind of get a really fundamentally decent understanding of both the basic space weather concepts and then the second chef, which are more advanced concepts, then this will walk you through it, right? And you will be very, very well schooled in basically conceptual space weather, and across a very broad set of disciplines, right? Because there's far more than just getting a PhD in space weather. That doesn't work. You can get about 30 different kinds of PhDs in space weather, probably more than that actually, if you really wanted to dig into the minutia. So this is what this set of courses do for you, is they kind of give you a really broad brush painting, but a conceptual physics painting of all of the phenomena from sun to mud. Okay, and they do form the foundational courses of an accredited university graduate curriculum program, or graduate curriculum in space weather communications. And yeah, so you are getting a really intense set of teachings from this. And it would not be possible if it weren't for all the people behind me, right? So I have to thank especially my steering committee. They're the ones that have really helped make sure all of this has happened. Oh, I've got an overlap there. Sorry about that. Lourdes and Nick Gaspard are kind of overlapping each other. But if it weren't for these folks, I would be lost, really. They help steer the ship. They kind of help guide where the community is going. We meet once a month. Some of these folks up here, I actually meet with more than once a month, or I do things with. You guys might notice Tomorrow's on here as well. Some of you watch the Tomorrow channel. Really, they're kind of guiding where the Space Weather Woman endeavor goes, what we're going to tackle next, how we're going to tackle it. And it's a lot of fun being able to learn from them. As much as I teach them, I learn from them as well. So if you want to be a bigger part of this community and really not just bend my ear, but help shape and guide how the future of this community evolves, please come on board, take a look, see what you can do. And of course, my mini course patrons, you all are the reasons why I'm able to do this, right? I'm able to teach you. You've helped me get to Millersville. You've helped me figure out what the curriculum needs to be, because ultimately I answer to you. And really, as we build the field of broadcast space weather, we need to answer to all of the user communities and the stakeholders. And that's who all of you are. And I'm so grateful to every single one of you. New members, you may not see your names up here yet, but you will soon. I guarantee it. So thank you for all of this, you guys. I really appreciate it. And yes, say hi to Jerry, Ryan, and Mike Richardson. They are the moderators for today. They're always the moderators for our YouTube classes. If you guys have a question and I don't answer it right away, ping them. They will get my attention, because anytime I see them posting, I'm always looking. So they will definitely make sure your question is heard. And for those of you who are Patreon members, go ahead and post in the Patreon feed if my question, if I don't get to your question in the YouTube feed, please put it on the Patreon feed and I will answer it in text if I don't get to it today accidentally, because sometimes the stuff scrolls by really fast. So thank you guys. I'm so glad everything is working. Oh my goodness, no one's going, your audio's out. I'm not getting phone calls. This is wonderful. Okay, so let's, without any further ado, I'll just give a really short review of the prior two courses. This is now the third in this ground-based, the ground level effects course, set of courses. And so I'm just going to give you a tiny bit of review because I really do want to focus on what geomagnetically induced currents do. But in order to really understand that, we kind of need to know why, where to come from, and how do we measure them, and that type of thing. So over the last two courses, really, we've been talking about current systems, right? So here's part of that second chef. Really, that's almost the whole thing of the second chef, is this Earth's magnetic system. And this is kind of a cutaway slice of it down the midnight meridian and then through the equatorial region. Here's Earth down in here, right? So the system is massive, comparatively speaking. And it's just a big particle accelerator that just scrambles anything that comes inside it. We've long since talked about how solar phenomena enter into this system. It's not from the nose, right? Most of the time it's from the tail, unless the field points a different direction. And then sometimes it's from the nose, but more close to the cusps and out here. So it's not intuitive necessarily, unless you're familiar with solar phenomena and magnetic fields. It's not necessarily intuitive how this stuff comes in. But at any rate, as it comes in, what happens is that you get particles that get accelerated. You get, and those particles, they're all charged, right? So they create electric and magnetic fields of their own. And they create current systems, okay? And so we've got lots of different current systems. Field-aligned current systems that sit really out on the outer edge of this stuff, and therefore they map to high latitudes. We've got current systems that are a little bit more protected, closer to the heart of the Earth's magnetic system, which isn't perturbed nearly so much, but when it gets perturbed, oh my goodness, it's massive, right? And we're talking like things like the ring current, for example. And so when we, and there's other current systems, but remember, all of this magnetic stuff and the current systems that are locked into the Earth's magnetic system, there is some order. There's some method to the madness, in a sense. We can actually kind of separate out, not perfectly, but we can separate out which current system we're looking at, just simply by looking at the magnetic field of the Earth's magnetic system and how it maps back to the ground, right? So when I take a look down here, for example, remember we talked about L shells. Remember, everything in the Earth's magnetic system is ordered by L shells. As you move out an L shell, right, bigger L shells. L shell is just simply the distance measured in Earth radii, the distance in the equator, in the equatorial plane, magnetic equatorial plane, the distance that a magnetic field line extends past Earth. So you have smaller L shells in here, right? L of 1, L of 2, L of 3, all the way out to possibly around L of 15 maybe during quiet time. L of, a lot less than that inside of geo orbit when there's a big storm coming. And a geo orbit is L of 6.6, okay? But all of these L shells, which basically talk about the Earth's magnetic system, right? I can't seem to do a class without having my slinky nearby, right? Here's the heart of the Earth's magnetic system sitting in here. Here is, one of the L shells, because it shows if you were to paint over this and create a skin, it would be a shell, right? And it's a particle accelerator. Particles sit inside this thing and accelerate. Remember, all of this is review. If you're not understanding it, go back and look at some of the other courses. This is just to kind of get everybody's head back in the game, okay? But as we move out to these higher L shells, right, the magnetic field maps to higher and higher latitudes. You can even see it here. Here's a really high L shell, and look where, if you follow that magnetic field line, it maps clear out to the poles. Right? Same thing with these field-aligned currents. That's why they map so far out in the Earth's magnetic system. This is the edge of the Earth's magnetic system. You can see this blue line, which is a region 1 current, maps way up here to the top of the auroral oval, right? And then when you go inside just a little bit, which is like here where the red one is, that's the region 2 currents. It maps a little bit lower. Can you see that? If it's resolved with the red line, it's resolved just a little bit lower. So high L shells are way out at the edge of the Earth's magnetic system. Lower L shells are a little bit further inside. And as you look at the Earth's map, right, where do the footpoints of those magnetic field lines go? High L shells are up high. Low L shells are down low, right? And if you were smart enough to put magnetometers in and around all these areas, you might actually tell that when a magnetic field line wiggle, right in this area, for example, you would know something's happening around L of 1,5, which means, or 1.5, which means something's happening way down in here. Some current system is causing magnetic field, perturbations. Okay, so this is why we cluster magnetic magnetometer stations at certain latitudes. Okay, remember this, of course, the reason why you see a tilt is because the Earth's magnetic system is tilted with respect to the geographic system. So the Earth's magnetic equator, which is not plotted here, but it goes like this and dips down and back up. Okay, it's just like one of these blue lines is just lower. Okay, so hopefully you guys remember that, and because we're going to use that again a little bit later when we talk about GICs and how and some of the work that's being done, some of the amazing work that's being done, and yeah, and we'll see how far we get today. Hopefully we might get through the whole thing. I'm not sure. Okay, so hopefully this refreshes your memory a little bit, right? Because now if we talk about different indices, let me just go back for one more second. We talk about different indices. So for instance, this is a KP. Okay, this is a map for KP. And if you go to Potsdam, you can actually take a look at all these maps because they actually have them up. It's a really great website for learning about the indices and where the magnetometer stations that feed those indices are and what they do, why they're there. It's a really great place for a lot of that historical information as well. But remember, different indices are set up at different latitudes for different reasons, right? The KP index, for example, which is one of our longest and most well-known, probably the most well-known index of space weather, it's a mid-latitude index. In other words, it uses some things that are up high, like in the auroral electrojet, almost there, subauroral, but somewhere close in there. But it also uses stuff that's a little bit lower latitude. It's what we call a mid-latitude index. So it doesn't capture necessarily just the ring current. And it doesn't just capture field-aligned current, subauroral, electrojet region. It captures kind of a mishmash, kind of a little bit of both, right? And the big difference in that is that when you have the high L shell stuff, right? That's the stuff of the Earth magnetic system. The Earth is sitting inside this thing, right? It's the ball inside this. When solar phenomena hit the Earth's magnetic system, it's going to jiggle and bother the high L shells first and peel that flux back. Whereas the inside, the heart of the Earth's magnetic system is protected. So low L shells don't get all that much activity, not unless the storm is big and has managed to peel off, like peeling an onion, peel off all the outer high L shell flux and peel it back, right? And fold it back and fold it back and fold it back and kind of open up access to the heart. So magnetic activity, geomagnetic activity starts from the poles and then works its way down. So a mid-latitude index like KP is nice because it captures a little bit of the really crazy activity up here because this stuff is wiggling all the time. And the really quiet stuff down here, it's not really feeling it too much, right? So it's almost like a catch-all. I mean, and I'm sure some magnetosphere physicists would go, "Oh God, why'd she say that?" It is not a catch-all. You're right, it's not. But it's a nice kind of all-purpose index. And it's also, in this case, global. KP, P for planetary, it's global. So it's kind of a nice, I've used this later in the course today too, but it's a dipstick of health for the Earth's, for a geomagnetic storm, okay? And yeah, the indices are radically different. So for instance, the AE index, if you remember what we talked about not just last time, but the time before that as well, the AE index is something that's going to be quite active quite quickly. So for instance, this is 2017, this is May 27th, 2017. We actually had quite a bit. You can see the AE index actually kicked up quite a bit near the end of that day on the 27th. Well, the KP index, this is all it showed. See the green, right? Not much activity. Whereas here, you're seeing a lot more detail. Well, because all of the activity really, it wasn't storm level. This wasn't a storm. These were just some substorms. These are smaller, little bitty things, but they were affecting high L shells, which is what the AE index is for, right? And then, of course, when we actually got into the storm period, it just kind of blew up like crazy, right? Which is what we see here in KP, right, as a mid-latitude index. And then it quieted back down, right? But the AE index still continued, whereas here it kind of went back to green a little bit, okay? So this is high L shell, this is mid L shell, and then this is low L shell. During that period, DST just went whoop. Yeah, it's okay. A little bit of a storm, you know. We got a, what is it, down to, I should look here. Oh, about 100 minus 110, 120 maybe. So we had a little compression up here. We had a little dip down here. So we had a little sudden storm commencement and then a bit of a geomagnetic storm. And as you can see, KP says yes, there was a geomagnetic storm because you can see it in red. But it really, on the grand scale of things, you know, big storms a big storm would be down here, would have a DST that dropped clear down here. Because remember, the DST is measuring the ring current, right? The heart of the Earth's magnetic system. So it's going to stay pretty quiet, right? It's not really going to be perturbed like the outer magnetic system is, the outer part of it. So when you're talking about field-aligned currents out here, those current systems are going to be disturbed like crazy. AE index, right? KP is kind of in between the two. And then DST, that's the ring current inside. That's not going to care about substorms. You think DST cares about this stuff? You think it cares about this stuff? Not at all. All it cares about is just this tiny little piece right in here. maybe this in the recovery, but not too much. Okay. So again, it's the different current systems are captured by different magnetometer stations located at different L shells or different latitudes on the Earth's surface. Okay, but you'd think, okay, well that's perfect, right? Well, no, not necessarily. You should always just look at AE, right? Because then you really know when things are happening. Not really, because AE can get completely saturated and just become a total disaster, a mess. You can't really make much sense out of it. During the Halloween storms, right, you can see the same kind of idea, is that KP just went ballistic. Now, granted, I'll show you in a minute that, you know, this is resolved. This is real-time stuff. And so the flat plots that you know, work typically well for smaller storms get so disastrously bad, you know, overwhelmed by you know, by real-time measurements when the storms are massive that, you know, it becomes unlivable. But as you can see, KP really is showing some serious storming here. Basically two big, you know, almost three big peaks. You got one, you know, which was the impact, and then a storm built up again, dropped for a little bit, probably northward field, either that or a second. If I recall, there are so many CMEs in this. This was probably a second CME hitting, so an ICME hitting. And you can kind of see that. You can kind of see that there are 1, 2, 3, you know, things happening, right? You see it a lot easier in DST though, but look at DST, look how far down it goes, right, compared to this. This is just a little bit of perturber, but this is, you can see very clearly what was going on. So there are times when you want to switch to, let's look at the heart of the magnetosphere. And there are times when you'd rather just focus on substorms and smaller stuff, right? Whether or not this causes a massive issue with GICs, we'll learn, okay? Or does it take one of these, right? The big thing that we're learning is sustained impact. So stuff like this can, because it's sustained, right? If you popped up to a G2 or G3 level just momentarily for an hour or two, but didn't stay, not so much. Something like this, where not only are you high at KP or high or deep in DST, you know, because you know you're hitting the heart of the magnetosphere now, but it's sustained over many hours, right? Each one of these bars is 3 hours. Then you know, this of course is going to impact the grids quite severely. This, not so much, but not necessarily, what should I say, debt-free? Not completely sweeping by without having some kind of issues, especially at higher latitudes. But we'll talk more about that in a sec. So hopefully, does everybody remember all of this? This is all stuff that's review. This is stuff that we talked about in the last 2 courses. Hopefully, because that's really all I wanted to talk about. Oh, I will do that. That's really though all I want to talk about is just that for review. All this plot is, this is just a plot showing that AE can be resolved. This is for 2003, so you can clean it up. It's not like you can't clean it up. It's just which one is this? Is this AE? Here's AUAL, and and that's the this is the ASY plot. Not exactly the same as that, but anyway, I did want to show that you can clean it up, and you can see the axes, are now over 2,500. But my goodness, it's just so, there's just so much going on that it's actually at this point you really kind of already know that you're almost sitting in open field. The Earth's magnetic system's got so much flux peeled back. You really should be paying attention to what's happening down at lower latitudes and what's going on with the ring current, because this is at least for space weather forecasting, it's I mean, and even now casting operations, that type of thing. It's not really all that useful. All right, let me take that off. Any questions on this, guys? I see lots of writing. Carlos has been writing a lot. When double layers get breached by a volcanic eruption, oh my goodness, a space rocket. Look, I am in the middle of something. You guys are really having a good conversation. I love that. Okay. And yeah, if you have any questions, ask me now before I jump into the new stuff, because we're going to start talking about applying this information and showing you a bit more about how the electric grids, why they're susceptible, what the issues what kind of issues occur, how do they couple into the system, that type of thing. So it gives you a better feel for it. You remember the storm of May? Oh, you do. Crazy Aurora, New Zealand. Yeah, I believe you, Edwin. That's really cool. There were some power issues regarding that, and I think I will show those if I remember my the slides that I put together yesterday. Let's see. Okay. What does DST stand for? Disturbance Storm Time Index. And yes, that is in the last couple classes that we've had. Disturbance Storm Time Index. And the reason why it's a negative index, you notice all the numbers go down, is because the direction of that ring current here actually goes, the electric magnetic fields are coupled. And if you have an electric field, especially, well, if you have an electric field and it's moving, you are going to create a magnetic field. And in this case, the electric field, the way it works with a ring, anytime you have a current in a ring, it's going to induce a magnetic field that is perpendicular. It's basically sitting in the center of that ring. Okay, so if this is the electric field, you're going to have a magnetic field that goes straight through that ring. And obviously the direction of the current dictates which way the magnetic field goes. Does it go straight out or does it go straight in? Well, that's dictated by the direction of the current around the ring. Okay. In this case, as this current gets ramped up, right, because you've got Earth's magnetic field as a particle accelerator, right? If I take Earth's magnetic shield and I stick it like this, right, this doesn't look too different than from CERN, does it? Right? This particle accelerator goes round and round and round. So you imagine particles trapped inside this, and they're going round and round and round. Now, granted, they're bouncing and doing all sorts and drifting, but they're going round and round and round, and they're getting accelerated to higher and higher energies because the Earth's magnetic system is getting energized and compressed and all that stuff. Stronger magnetic fields can create stronger acceleration. So the particles are getting more and more energized, and you're getting more fluxes because you're getting this stuff pumped in from the big solar storm, the big CME that's hitting, and it's pumping this stuff in, it's shooting it up through the tail, and it's populating in the ring current. As that happens, you're upping the strength of that current. Well, it's going to up the strength of any magnetic, any magnetic field it's going to induce. Well, that magnetic field is actually the opposite direction of the Earth's magnetic field. So the Earth's magnetic field has a north pole here and a south pole here, right? Well, this current induces a magnetic field that goes from north to south this way, and it serves to depress the Earth's magnetic field. Come on. That's why this goes down. That's why it's negative. Okay? So this is the depression of the Earth's magnetic field. So that's what we're measuring when we're measuring the disturbance storm time index. We're measuring the depression of the Earth's magnetic system. But that only happens when you have a big geomagnetic storm. Big geomagnetic storms occur when you have a long duration disturbance, like a coronal mass ejection, that has the right magnetic field orientation to couple into the Earth's magnetic system and create one big thing. Okay, hopefully that makes sense. Right? The longer it couples, the deeper the storm. The stronger you make that ring current, and the more it can depress Earth's magnetic system. Okay. Is aurora color related to altitude? Yes and no. It is because the atmospheric chemistry changes, right? But it's also related to energy. Aurora color, most of it's done by oxygen, actually. Nitrogen gives you the bluish purples, but oxygen gives you the greens and the reds. And then pretty much the combination of all of that can give you the rainbow, right? I mean, when you think of a television, remember the old projector TVs? All you needed was a red, blue, and green projector, and it could, make all the colors that you need to see. Well, same kind of thing. The aurora can make rainbow because you've got the blue and purple with nitrogen, you've got the red with oxygen, and the green with oxygen. There you go. You're good. So now we can, eventually, if we can imagine, we could just watch our television in the sky. Just kidding. So if you had a compass at the ground level, would you see that? If it's sensitive enough, well, no, a compass, no, probably not. I mean, the problem is that compasses are not going to measure intensity, right? If you had a magnetometer at the ground, sure, because that's what they're getting this from. They're getting these from magnetometers. You have to have something that's going to measure the intensity of the magnetic field, not necessarily the direction of it. And compasses do go a bit nuts during a geomagnetic storm, but they have to be extremely sensitive and calibrated well. So a handheld compass, I don't think it would necessarily show you something like that. Okay. No, will the eruption of Mauna Loa cause a pole shift to move faster? No. The pole shift is moving. It's all due to the core, the iron core that we have. The Earth's atmosphere is going to move. Even the charged particles are going to be moved. Are going to move if they're going to move in relation to the Earth's magnetic system. It's all going to be driven from the core, not the vice versa. Let's see. Thank you for the compliment. Okay, good. Hopefully everybody got this then. We're ready to move. Okay, we're ready to move forward. Okay. So we're going to start getting into a few things. And really what I'm hoping to accomplish with this class today is really to kind of like talk you back from the ledge in case you happen to be at the ledge. There is so much hype when it comes to geomagnetic current, or geomagnetically induced currents, or what are called GICs. And it's all because of the grids, right? It's all because of the grids. It's all because of the superstorms. It's all because there is a real threat, right? But sadly, in order to get policy written in Washington, oftentimes you must invoke these massive extreme events that affect this kind of critical infrastructure, right? And so you get assessments done like this. I mean, this is how you can commission assessments, is you have to alert them that the possibility of everything failing is real, right? And that's great and that's wonderful, except from an astrosociological perspective, say that through 10 times fast. From an astrosociological perspective, it causes a lot of fear, right? A lot of panic and a lot of fear. Um, and in the in the public's mind, and it's really unfair because it's like the analog in terrestrial weather is like, in order to get policy written about disaster relief for hurricanes, you have to invoke a hurricane. You have to talk to the government about hurricanes, right? And we know enough about weather in our daily lives to know that not every rainstorm is a hurricane. As a matter of fact, most of the time hurricanes don't happen. But they do happen, and we've seen enough of them, and we see the devastation that they cause to know to take them seriously, right? Not to switch off about them, but to take them seriously, but also to look at them as being surmountable, right? It's just something you live through. I mean, if you live in New Orleans, I know way too many people who live in hurricane ravaged areas, people who have lived through Katrina, and they will not leave, right? They may get panic attacks when there's a big when they look at their Doppler radar and they see a big monster coming, but they know they will live through it. They know they will survive it. They know it doesn't mean Armageddon. It's just a hurricane, right? We don't In space weather, we're not there yet. The sad thing about space weather is that when we live through a big vent, most people don't even realize it, right? The people who are sweating bullets are people who are dealing with the critical infrastructure. They're the ones sweating bullets, right? The rest of us just go, oh, our power went out. Dang, these stupid power companies, wish they could get equipment that worked, right? Stuff like that. Or, my GPS, why isn't it working? This stupid phone, right? We don't realize necessarily that what we're dealing with is the space weather version of a hurricane. And so when we get on the news, when we see on the news, or we see these types of assessments being done, we get scared to death that, okay, because they're seeing, oh my gosh, we're going to be blown back to the dark ages, or oh my gosh, they're going to have transformers that are going to be down for 6 months to 2 years, and then we watch the History Channel, we watch the Discovery Channel, we see insanity, people talking about microflares and supernova and mega flares. That's what it is. Micronovas and mega flares, and they're talking about Alpha Ceti and stars that are in light years away, and they're young stars and they're massive stars, and look at this, they light up like a Christmas tree and have these mega flares, and if that happened with our sun, Earth would be, the sun would suddenly get like 100 times brighter. I think 78 times brighter was what I remember seeing Phil Plait talk about. And it would get that much brighter in 2 seconds or 2 minutes or something, and the Earth would just be, and it's like, oh, for goodness sake. And they said, and then the storm, if they had a geomagnetically induced current from this Carrington class event, my goodness, it would knock us so far back into the dark ages, the cars would catch on fire, and people would be fighting in the streets, and there'd be no water, there'd be no power, there'd be no, and it's just like, oh my Lord, right? You might as well write Santa Claus and write God, because we're done, right? Stick a fork in us. It's over, right? And then people switch off, lights out, done, right? People don't do that with hurricanes, but they do that with the space weather equivalent of a hurricane because of how it's being invoked. And that is the problem that I have. And anybody I train they're fighting this. We're constantly fighting this. And so I'm not going to make this a class about astrosociology, but I did feel that I needed to step in and kind of mention some of this stuff just to couch all this in the right frame of mind, right? We need to talk about these intense events from at the level of intensity, the fact that they're extreme events, in order to get funding thrown at it and get people to take it seriously. But if the public thinks that this is the only thing that happens, well, we're in trouble, right? Because it becomes this Hail Mary. And that's not what space weather is. Most of the time, it's just another sunny day in space. And even when it's not a sunny day in space, it's just a drizzle. It's just a rainstorm. It's not a superstorm Sandy. Okay. But we do need to prepare for them. So there are a lot of papers that are available. This is one of them, for example. They're in open literature. You can read all about them, and I will show you just a few of them. I'm not going to dive into them in depth because you can do that on your own, but I wanted to be able to show you some of these. This was done in 2018. Here's a nice one, geomagnetic storms in the U.S. power grid. This gives you some good information as well. Some of these have been done a long time ago. Some of these have been done recently. Here's one in 2020 done by Mark Glauby. All with the North American Electric Reliability Corporation. We have the NERC and the FERC. The FERC is FERC. It's the Federal Electric Reliability Corporation. And the NERC is, I think it's private, and then FERC is federal. And they all work in tandem along with other consortiums like the PJM consortium. And in this case, I'm going to be mostly focused on the North American, meaning so United States and Canada mostly. But I will talk a little bit about Britain, for example, their national grid, and some of the work that they're doing. And I'll even poke a little bit at the Japanese. Okay, I don't mean poke fun, just poke, talk about, right? Because there are some real serious issues that go beyond just the grid, but that talk about geomagnetically induced currents and how they propagate, how they work. And so you'll see that a lot of the work that's being done ends up being extremely useful for other infrastructure that also has to deal with GICs. Here's another one. Okay, here's one from 2011. I mean, people have been working on this for a very long time. And then we'll actually dive into this one to some degree because I have to say, John Kappeman was probably one of the guys that really started it all. As a matter of fact, I'll do something unusual, which is to play a video that he did. I'll probably have to put my microphone up to the screen. I wanted to be able to play. This is the reason why I was hoping to be able to use that other cam link, was that I wanted to be able to play this video that I have with a microphone plugged in automatically, but I'm not sure I'm going to be able to do that. So anyway, we'll figure it out. At any rate, so there's a lot of information out there that's been done. I mean, John Kappeman was doing this back in 2008. So, we're talking more than, what is that? More than 10, 14 years ago, almost 15 years ago now. And it's really, this is kind of like set the stage for a lot of the other work that's been done since, because he really kind of helped, for the first time, helped us really understand how incredibly susceptible our grids can be to the very large events. And he analyzed in incredible depth the 1989 event. So we'll talk about that. Okay. Yes, I see that you're in Israel and we have the same grid system as in Europe. Yes, it doesn't matter. Don't think that if you're at 60 hertz, 110 volts, 60 hertz, or 120 volts, 60 hertz, or 220, and at 50 hertz, it doesn't matter. GICs don't care. They care more about bedrock. And we'll talk about why this is. Okay, so I'm going to jump into it just a little bit. So imagine all of this, that coronal mass ejection. I love how, when we start getting in, this is why you can get a PhD in so many different areas of space weather, is that when we talk about ground-induced, or geomagnetically induced currents, the issue is that it makes everything else kind of be nothing, right? The coronal mass ejection interacting with the Earth's magnetic system, something that took us like 20 courses to do, is now reduced to 3 little lines. Right? It says CMEs emit particles that can travel toward and interact with Earth's upper atmosphere and disturb its magnetic field, which is shaped by the background solar wind. There is very little about this statement that is correct. It's not the particles that are interacting with the Earth's magnetic field. It's the magnetic field inside a coronal mass ejection that is doing that. And the CME is not necessarily shaped by the background solar wind. I think they're talking about the Earth's magnetic system being shaped. Okay, don't know. But it's not just 3 little lines. So luckily, if you have all been following the courses, you realize that, when people are very, very skilled at this area, they're not so skilled here, right? Which is why space weather is from sun to mud is so difficult, because there's just so much to know. It's hard to be really savvy at any depth, deep level in more than just a couple of these fields. But to take it kind of, down to where we are, right? When we're talking about this stuff, right? They're talking about the CME time varying ionospheric current, right? We're actually talking about the magnetic field wiggling, okay? Creating, and these are like electrojets, okay? And you have the magnetic field wiggling into the foot points all the way down, and it's creating these magnetic field perturbations, horizontal perturbations. Remember from the last couple classes, we talked about the H component being a huge part of this. So when we have the magnetometers on the ground and they're showing deviations, right? They're showing deviations in the H component, in horizontal components of the Earth's magnetic system. Okay. So this is what they're really trying to talk about, is that these currents can drive time-varying magnetic fields. We know the source of the currents, the original source of the currents, is not in the ionosphere. It's not where it happens. It's actually out in the Earth's magnetic system. Right? So when you have this kind of stuff happening, you end up inducing currents in the ground. It's really kind of inducing potentials. Okay. And yes, we start using the word magnetotelluric currents. Okay. The magnetotelluric field is a more akin to geophysics and geology. Okay, so we're really getting down into the geophysics now. And it matters how much metal do you have in your rock? How conductive is your rock? The more conductive it is, the less the current has, or the less the potential has a problem moving through the rock. If you have very resistive stuff, rock that doesn't really allow current to flow very easily, well, that current is going to be pretty excited to get out of Dodge and find some other way to flow, because the magnetic field up here wiggling like crazy is telling it, I need to flow, right? It's trying to obey the magnetic field because the currents that are the potential that are being induced in here is trying to get electrons to flow. It's trying to get these charged particles in the rock to move. Okay. Well, what happens is that it looks for anything that's more conductive than the rock that it's in, right? Electricity always takes the path of least resistance. Anybody who's ever had stuff short out knows exactly what I'm talking about. It will easily short out if it can find a short path, right? Path to ground or path to anywhere else. Well, it's doing the same thing in power systems. So when you look at a power system, you have basically, in a nutshell, right? We're taking a look at this very broadly. You basically have three different sections, okay, to a to a power system. You have the generation section, right? This is where you have your power generation from whatever facility, however it's being generated, whether it's burning fossil fuels or using, turbine engines for water going through a dam, however you want to do it. But you're going to have a generation system, and that is going to be connected with a substation and a transformer that's going to step up the voltage of that. And the reason why it wants to step up the voltage is because it wants to, basically low voltage systems are very inefficient. High voltage systems are much more efficient in terms of passing current along a wire. Okay, so you don't want a lot of loss in your current. So that's why they always step up the power, step up the voltage in these transformers, and then put them through the very big, tall, the massive, tall wire system, right? Not your little teeny tiny ones that serve residential sections. Those are actually stepped down. They're a lot lower voltage. They're more lossy. But the big ones, the intercontinental big transmission lines, the ones you don't want to be around, because there's a lot of noise from them electromagnetically. But those ones are very efficient. That's why they can transfer power across, very long distances with very little loss. But in order to do that, you need a transformer that's capable of stepping up the voltage. These are the ones that everybody worries about failing, the ones that cost a lot of money, the ones that you basically need to break streetlights in order to get them through, get them to their destination. And that's part of the issue when they talk about replacing these things. Just even if you had them already and waiting in some storage facility somewhere, just getting them to their destination is a major undertaking, because most systems, they're so big that most of the streets in neighborhoods uh, are not made to handle these the paths of these transformers. So it's really cumbersome to try to move them from place to place, and you have to be extremely careful how you do it. Anyway, that I'm getting off topic. But what happens with these transformers is that most of them, right, well, all the big ones, are grounded. They've grounded it right into the bedrock, which is great, except when you have bedrock that is not very conductive. Because when a big geomagnetic storm occurs, and now you've got the particles, the charged particles in here trying to move, and they can't move, but they see this ground wire, and they sense that there's this really cool transmission path. It's like, oh my gosh, it's a super highway, right? This is like a traffic jam on a side street, and this is like, the Autobahn for them. And they'll just jump right up in here and go, oh yes, we're golden. And they'll sail, right? The problem is, as soon as you jump particles in here, you got a current source this poor transformer was not expecting. Neither were the transmission lines, neither was a power generation station, neither was anything else connected to it. Okay? So this is where you start having problems where coupling with GICs occur. Right? So you have this big long transmission that can be hundreds and hundreds of miles of unbroken power lines that can cause real issues for lots of current, because if you have thousands or hundreds and hundreds of miles of unbroken transmission lines, then you're covering a very large distance. And the problem is, if the bedrock all under here is not very conductive, well, you've got a lot of potential building up over time or over space, right? This is why grids are so susceptible. It's not, people say, oh, well, my phone is going to bust, or my computer's going to go, or my car isn't going to start. The battery's not going to start. And I'm like, no, that would be true if your car or your pacemaker or your computer were the size of Lake Michigan, possibly. But if it's a lot smaller, then that's not going to be a problem. The reason why is because Earth's magnetic field really, as it's inducing currents into the rock by shaking and wiggling, creating this kind of thing, this time-varying magnetic field. This is not a very strong magnetic field, not at all, right? I mean, Earth's magnetic system is only about as strong as a fridge magnet, but it's a fridge magnet the size of Earth. So over the course of hundreds of miles, the tiny little inductions, right, add up. We call that integrated, right? So you have this plus this plus this plus this, tiny bit by tiny bit by tiny bit by tiny bit doesn't mean all that much to a small thing, right? A computer, a pacemaker, a car battery. But to hundreds and hundreds of miles between big transformers with this Autobahn free zone, toll-free road going that far, and all of these particles can take part of that, and you can look at the potential difference, the amount of particles, which way the current wants to flow from here to here. You only look at point A and point B and look at the difference, and all of that energy from that huge distance now can be moved through this. The particles go, yeah, I'm on it, right? So that's the problem with having really long transmission lines, is it allows all of this stuff that's going on underneath it to possibly couple up in here or couple up in here, okay? So you have a step-up transformer, in this case, a step-down transformer, right? And then you have distribution. So now all your residential lines, right, the ones that you're used to looking at, these aren't the ones necessarily that kind of gonna, you're not going to look at them necessarily and go, oh my goodness, these are the ones that are got these huge GICs. No. This is it's this part of the system that's the problem. Okay. This is where all of the, I don't want to say it's not where it's all the magic happens, but this is where the source of GICs become problems. Obviously, the issues come in here and mainly in here, or mainly in here in the transformers, but also you'll see some in here too, and you'll see why in a short bit. Okay. Hopefully, did I make that clear, reasonably clear, right? That it's really the transmission part of it, and that it's not The Earth's magnetic system isn't coupling straight into the wires. It's down to the ground, and it's the rocks. It's the rocks' fault. It's Earth's fault, right? It's electricity trying to find the easier path. It doesn't want to move through rock. Electricity doesn't like rock, right? But if there's metal in that rock and there's free electrons, well, it's a semiconductor in a sense. A lot of rock is. So it's not a total, and so you'll have enough free particles to be able to get there and start moving elsewhere. Okay. Um, hopefully that makes somewhat sense. Okay, and we're gonna start diving into this a bit more. So to kind of summarize what I just talked about, right? Electrical grid provides an alternate current path other than going through rock. The less, and obviously the less conductive the rock is, the more that electricity wants to find an alternate path. Okay, and these fields, although you've got a wiggling field, you're going to create a current from the rock. You're going to create a current that is essentially DC current. Okay, it's not going to be alternating. Remember, the current systems that we're in, these power lines, that's alternating current. And that's partly where things get kind of weird. It's kind of cool, but it's kind of weird because you'll learn that pretty soon you'll learn that our power grids, the way they're built, and the fact that we use alternating currents, and the fact that we use capacitive storage and we use inductive storage, and I won't get into what those things are too much. But the fact that we use the system the way we have it, that there's a kind of a built-in storage ability. It's kind of springy, okay, and that's where reactive power comes in. It's like this, and you kind of need it. I mean, if you had a rigid power system like just a DC power source, it wouldn't be able to handle changes in load, changes in the usage of that power, and it sure wouldn't be able to handle GICs very well. So in a sense, we've kind of helped what we have built in to kind of help us with these with variations in power, in our power, in our distributions, and just in our generation and in our distribution, and even in our transmission. The fact that we've introduced, the fact that we have that ability to store some of this power is, and have it be reactive and have it be springy and have it be able to handle the variability to some degree. That is wonderful. It saves us to a great degree from GICs, to be totally honest, because GICs are happening all the time. Anytime we have a solar storm hitting and it becomes a geomagnetic storm, you're going to get GICs. They're just really low level. And so the grid goes, yeah, no big deal, right? But it's only when they get big that becomes a problem. And so really our grids really are made to handle GICs. It's just sometimes the GICs are stronger than we can handle. Okay, so don't think that the grids are that susceptible that they're going to go down. As you'll see very quickly here, I'll talk about it. You'll see how, hopefully if I can explain it, boy, it's going to be fun. You'll see what I'm talking about, that they really are kind of springy, and they really are designed quite well for most GICs. Okay, anyway, so obviously, when we talk about this, GICs are greatest in the transmission lines that are. Why is this thing going crazy? In the transmission lines that are, obviously stepped up in voltage. Those are the long transmission lines. I'm sorry for all these notifications. Doesn't look like anything's wrong. Just my phone is just going nuts for some reason. Okay. Probably a lot of aurora right now. For those of you who know, we've got some good fast wind happening. So we talked about the fact that when you step up the transform, go through a step up transformer and then you go into the high voltage lines, that's where GICs occur. It's really having to do with the longer transmission distances. That's why we get these problems. And then, of course, the electricity then can couple in and out of the bedrock from the step up and step down transformers. Because we've talked already about the Earth's magnetic system and how the second shift couples to the ground and how magnetic field moves, that the higher latitudes are more susceptible because they're higher L shell, right? So you understand this. depended upon geography, right? Geology, getting a better understanding because we understand that the bedrock itself is the source of where the current can possibly flow. So the more resistive the geology is, the more resistive the rock, the more the electrons, the more that potential, that current is going to want to find an alternate path, right? So if you have a highly conductive ground, you're not going to have as much problems. Yeah, again, okay. Now we're going to talk about half cycle saturation. I'm probably not going to bring up half cycle quite so much, but we'll see. We'll talk about that when we talk about reactive power. And I borrowed some of these things. These are just things I wanted to make sure I touched on. Obviously, the storm intensity, we've already talked about this. We're talking about geomagnetic storm intensity. And we will talk about orientation, not just from a magnetic field point of view, but my goodness, at the very end of this, I'll show you some interesting work that's been done just recently in the last couple of years, even about shock impact and the orientation of the shock as it hits Earth's magnetic system, how it actually can cause GICs to be different and how they propagate. So we're really beginning to get really good because we now finally have so many magnetometers. We're turning what used to be just like the cosmic ray spaceship Earth that the Bartol Institute used to talk about all the time, spaceship Earth with cosmic ray monitors everywhere. We now have magnetometers that are very much in a very similar fashion. So we have the spaceship Earth being kind of reinvented in terms of magnetometers, and they're all now providing real-time information. And we'll talk a bit more about that. But it's allowing us to make really interesting science advances that I just maybe 10 years ago would never have thought possible. Yes, we're going to talk about the increased reactive power demand, which then causes the power output to drop. We'll talk about that. And that, of course, then causes a chance for the voltage collapse that then can cause cascade failures, blah, 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 blah. We're going to talk about harmonic currents and, yes, how the harmonic currents can actually create heating in transformers. And just in case you wanted to know where I got all this, this is from Jeff Fleeman's work that he did back in 2013. So, a lot of this stuff is stuff that we know quite well. And it's really, we're dealing with either electrojet, we're dealing with magnetic field from big storms and inducing these ground potentials, right? And sometimes they're called ESPs, just so you know. It's not this, but when you see it, invoked in geomagnetically induced currents, or GICs, you will see there are three acronyms that you will see quite frequently. GIC, ground or geomagnetically induced currents, not ground induced currents. Sometimes I make that mistake just because I think ground, but it's geomagnetically induced currents. And then GMD, geomagnetic disturbances. Okay, GMD, that's basically talking the geomagnetic storm, okay, from a CME. And then ESP, Earth surface potentials. Okay, so we're talking about this stuff. Okay. Oh, right. And sorry, I did not define that. I should have put that in words first. But during a GMD event, GICs can cause, see how you can get laden with acronyms really fast. You can have the harmonic currents leading to voltage instability, localized heating of oil insulation or windings in transformers. Yes, we're going to talk about that. Damage to winding insulation, we will talk about that. I will talk more about that just in words. I don't have slides to show that. That was a good conversation I had with Robert Fenton, who really helped me understand what reactive power is. Then you have the loss of reactive power capacity because things get taken out of the loop, and right at the time that you need more reactive power, and it's actually causing reactive power to be chewed up, or not chewed up, but just forced upon the system. We'll talk about that in a second. And then you have also protective relay system malfunction that oftentimes causes this, because the relays are meant to, in power systems, relays are meant to shut things down when something goes wrong, or when something has harmonic currents, or something's overheating. So it automatically shuts things down, and that is what you don't want, because when you shut things down, you lose your ability, you lose your reactive power capacity. You lose the sources of reactive power, and that then can lead to cascade failure. So believe it or not, it's non-intuitive, but the reaction to a big storm is not to shut the system down, but to turn off all the protections so that the system stays up and rides through it no matter what, and just grins and bears it. And so what it begins to teach us is that we've got to understand these transformers better and what their load is and how we can mitigate that and what we can do to see how bad a transformer is getting, how overheated is it getting, what's happening to the transformer while it's undergoing a GIC, or undergoing GIC effects, so that we don't take it offline prematurely, but we do take it offline before there's a horrible cascade, and we try to mitigate in the process. Okay, because remember, when geomagnetic storms hit, it's not going to be the same everywhere, right? Even in the United States, we're going through lots of different L shells. So there may be the capability that you pull some things offline up here, or some things offline where there's high levels, or where the ground conductivity is such that there's a lot of coupling into the lines and the GICs are bigger. But then other parts of the grid can help take an extra load because their transformers are not nearly as impacted. So maybe you can take a couple offline up here strategically because the others down here can handle it. Or maybe you can't. Maybe there's an older transformer that's having a lot more trouble because it's wet. Whereas this one over here is dry. It's a new transformer. It's dry and it can handle a bit more. We'll talk about that. Okay. This is where we are going now when it comes to doing research on GICs. Okay. And I bet you all of you guys who are learning this, you're going, you're probably happy right now that you're actually, where am I? Oh, not there. Not yet. You're actually happy that you've watched the other ground-based, all the second chef courses, because you wouldn't know nearly as much about the latitude dependence of GICs. You wouldn't know that if you didn't have these other courses that I've taught. Okay, so harmonic currents, that's a biggie, right? And a lot of people don't even realize that this is what happens. And if you guys ever want to, I've grabbed a few slides from Power System Operation. This is a channel on YouTube. Not a lot of dialogue, but a lot of good slides, and really, really some good stuff in there. I was actually quite surprised to find a YouTube channel that actually had that. But I thought, since this is a YouTube course, you might want to check this person out. Can't vouch for everything being correct, but I will show a few slides from this from Power System Operation, because the person, the author of this, put together some things that again are kind of at that 50,000 foot view. I'm not trying to dive into the minutia. If I do, I will very rapidly step way outside my expertise, and I don't want to do that. I only want to give you a feel for it. But again, any electrical engineers, please forgive me if I say things that are kind of blurring the lines. It's kind of hard to talk about this stuff without and simplify this stuff without kind of coloring outside the lines a little bit. It's just, science can be tough. Okay, especially when you get into the science of electricity, because sometimes it's just not intuitive. Okay, so harmonic currents are an extremely multifaceted problem. Anybody who's ever looked at stereo, amplifiers, look for things like total harmonic distortion, right? That THD. That's something that probably a lot of people have heard about. And you're always trying to get that lowest part of total harmonic distortion, and you want that. And the reason for that is it can be multifaceted. But believe it or not, that type, obviously things sound better when you don't have the distortion, because the higher harmonics, at least in audio, of course, can really make things sound terrible. An example, auditorily, from an auditory point of view, a pure tone, an instrument that's a pure tone, is a flute. If you play a note on a flute and look at it in an oscilloscope, it is almost a perfect sine wave. You want something that has a lot of high harmonics, a lot of really fuzzy type of notes that basically has the fundamental and then higher harmonic that is a little higher or bigger, excuse me, larger number of wavelengths, so a little bit more wavy, and then even higher waves and even higher and higher and higher. Those are harmonics. Every time you take a wavelength like what we show here and you cut it in half, let's say, so you have something that goes like this right through here, and it goes faster and faster. That those are what we call higher harmonics. And I'm not going to get into the details of that. That's that you can look for basic physics courses on that. But a flute will have only a single wave, okay, what we call the fundamental. An instrument, for example, that has lots of harmonics, not just the fundamental, but lots of other smaller waves on top of it, is a trumpet. Okay, think of the tone of a flute compared to the tone of a trumpet, and you get a sense for what a pure tone would sound like and something that has lots of harmonics sounds like, right? Very different. And you can tell a trumpet is a bit more brass. It's brassy. It's what we call brassy, right? It's more biting, right? A flute is very pure and calm. Well, most transmission systems want to be a flute. They don't want to be a trumpet. Okay, I mean that's the non-technical speak. GICs force a flute to become a trumpet, and I just made that up on the spot. I hope that works. Had no idea I was going to say that, but that's kind of what we're talking about. In this case, GICs, when you take a flute, which is this perfect tone, right? This is an oscillating current. Okay, this is an alternating current. What we have when you say 60 hertz in the United States, this means we will have one wave that starts here, goes up, goes back to zero, goes down, goes back to zero. Okay, so in other words, it goes up positive, right? I'll have a voltage or something that's positive, or a current that goes positive and flows in one direction. Then the current will slow down, stop, reverse direction, flow the opposite direction to the same amount, same level, same intensity, and then come back. That is one cycle. Okay, a 60 hertz current will do this 60 times in 1 second. Okay, that's a 60 hertz. 50 hertz current has 50 of these in 1 second. Got it? So, currents in current systems are moving back and forth very, very quickly, right? It's positive, negative, positive. It's kind of like a you're in like a paint mixer. If you're a good, right? No, but that's kind of what you're dealing with when you're dealing with alternating current systems. Okay. A pure tone would be a flute, doing it as smoothly as possible. Right? If you have a geomagnetically induced current, suddenly you're going to get a peak. Now, granted, these are big, right? We're talking about very, very large, 50 amps per phase, 100 amps per phase, 150 amps per phase are showing, really big currents being in geomagnetically induced currents here. And we'll talk about how, is this realistic? Okay, we'll talk about that. But this is what happens, is that suddenly, instead of this beautiful blue wave that you see here for the current, you suddenly have this tail, this really ugly horn. Okay, that's this harmonic. It's a shorter wave, right? You can see it's not as wide as this is. So it's a higher harmonic, but it's also offset, right? Now it's shifted the peak from there to there. It's moved it, okay? Hello, geomagnetically induced current. And it happens every phase, okay? And it can be strong. It can be quite strong. Power grids don't like being trumpets. They'd rather be a flute, okay? When transformers have this, they can get saturated very quickly, obviously, right? It's not ready to take that, let alone have it be off phase. It's ready. It was supposed to go down. Now it's going back up. What the hell, right? It's supposed to go down and be smooth over here, and it goes like this, and it's ready to go down again. What? It goes back up. What the hell, right? It doesn't want to do that. And if that translates into something mechanical, that's not fun, right? And we'll talk a little bit about that. Obviously, one of the first things that happens, heating. It's going to get hot. It's not working the way it's supposed to. It's taking more current, it's having more current being pushed into it. These are the particles coming in from downstairs, from the feet, from the ground, coming up right through it, right? This is the GIC. And obviously, if you have an automated protective relay, it sees this, it's going, oh my Lord, shut it down. What the heck? We have to stop this before it breaks something, right? It recognizes immediately, this is not a flute, this is a trumpet. We don't want no trumpets, right? No trumpets allowed. And so it will shut the grid down, or it'll shut that transformer down, or it'll shut whatever's going on, the source in that substation, let's say. Okay? It will go through its protective circuit, recipe and procedure, right? Because it's probably thinking, like in most cases, this is an isolated thing, right? It's only happening here. And there's something wrong with the system. We don't want to break anything. Let's just shut it down. The problem is that when there's a geomagnetically induced current, it's happening everywhere. So every single one of these relays is feeling the same thing. It's going, oh my gosh, my transformer just turned into a trumpet. My flute just turned into a trumpet. We got to shut it down. Wrong. Do not do that. So that's not one of the number one things that the NERC and the FERC said, is that as soon as we get a geomagnetic storm of a certain intensity, and so this harmonic current becomes an issue, right? Turn this off, because this is not going to help us. Okay, we need to we know what the problem is, and there's not anything we can do about it. And it's not that our machinery is acting improperly. It's not that we have a failure in our machinery. It's that the earth is coupling up into it. And therefore, doing this is not the right response. In every other situation, it is, but not in GICs. Okay. All right. So what is reactive power? We're going to talk a little bit about this. And I'm not going to talk about it in any depth, and likely you're still going to have a few questions here and there. And for those of you who want to continue further, my suggestion is to look it up. But we're going to talk a little bit about how reactive power helps alternating currents, circuits, grids, power grids, how it helps to make the grid springy, to make it be able to handle things typically like GICs or changes, variability in load. Okay, it's actually quite useful, and I don't. According to Fenton, he told me that it was actually reactive power was actually something that was created a long time ago when things were far more mechanical, and you had to have coils that could then spin. And alternating current systems were fantastic because if you had certain aspects of, and we'll talk about this in a sec, certain aspects of the current delivery, the voltage and the current delivery, out of phase with one another, you could optimize how a coil, like let's say in some generator, would be able to mechanically spin and make use of that energy. And I won't definitely go into the details of that, but it's set up a really interesting. It's set up in a really interesting thing, which is called the power factor. And I'm going to give you a few examples of it, and yet another YouTube site to go to, because there's a nice site called The Organic Chemist, I think is what it's called. Strangely enough, talking about power factors, I have no idea why, but nonetheless, it's cute. It's a cute site. But we're going to talk a little bit about the power triangle, and then I'm going to get off of it so that we can actually see a more, what I think is a more realistic, a more intuitive way of looking at it. But this is for those of you who actually feel a bit comfortable with trigonometry. Okay, sorry about that. For those of you who don't, I'll do my best. Believe it or not, the power triangle it's just a triangle. Okay. And the reason why I want to bring it up is because we're going to talk about phase angle just a little bit. And I just want to give you an idea of what phase angle is, right? We can say impedance for those of you who are familiar with that term, but for those of you who aren't, don't worry about it. But really, just like any triangle, that's a right triangle rather. We call it a right triangle because these two lines are like the corner of a room, right? They're right at right angles. If we talk about the true power that's delivered by a power distribution system, okay, we're just talking about a certain amount. Let's make it this long, okay? As long as this line is, okay? So I don't care, you can call it, 17, inches, 17 bat lengths. I don't care, 17 whatevers. I don't care. It's just this long, okay? You can actually have in an alternating current system, you can actually have the apparent, what seems to be like you have more power in your system than the power you can deliver. There's like a hidden amount of power. And the reason why is because you use something called capacitors and inductors. Again, once again, those of you who are familiar with that stuff, great. If you're not, don't worry about it, because I'm going to show you a different idea of how it all works. But that apparent power, right, see how long that line is? It's much longer than the true power, isn't it? Right? It's not double, but it's longer. And if you look at the angle in this right triangle, that can, in trigonometry, can actually define something. It can define a third length. Okay, so depending upon how big this angle is, if I lowered this angle, then this line would only be from here, from my arm down to the edge right here, right? So this would be a lot shorter line if this angle were smaller. If the angle is bigger, obviously this line gets longer, right? And you can imagine if this angle goes all the way up to almost infinity, well, then this line behind me will go basically all the way up to almost infinity before the lines actually touch. Where things become undefined, at least in mathematics, is when this angle, this angle goes all the way up to a right angle, and now you have a box with no lid, because these two lines will never meet each other. Okay, so you can break this whole system, right? And in actuality, in the power grid, that's exactly what they talk about, is that you have voltage collapse because you no longer have this triangle be a triangle. It becomes an open box. Mathematically, that's what's happening, or from a trigonometric perspective, that's what's happening. Strange how triangles and squares, open boxes, can actually, be an alternate way of describing something, isn't it? At any rate, so the phase angle, obviously, as you can tell, is extremely important. If you open it all the way up to 90 degrees, what we call half wave, you might remember me saying that before, you break the box, you break the triangle, right? If you collapse it down and make this angle go to 0, right, you also break it, clunk, because now that line, reactive power, is 0, right? It's just a line all the way across, and your apparent power now shrinks down to the true power, which is here, which becomes, again, broken. So in an alternating current system, you have a balance. You have this triangle that's kind of balanced, and believe it or not, it can wiggle, because you can change this phase angle. Okay, so the triangle's kind of always shaping itself. It's always kind of reforming and wiggling a little bit, and that's neat, because it's kind of shows you that this is what I mean by having a power system that are like our power grids are capable of kind of handling a variable load. They're able to kind of roll with the punches, just like this triangle would be able to change and reform itself, basically by simply not necessarily, by basically keeping this, no, I ought to be careful, by basically just reshaping itself, okay? You can keep your true power in as a locked down, but by changing your phase angle and changing your the length of these two sides, you can actually change the shape of that triangle completely without breaking it. Okay, power systems do that. At least alternating current power systems. For those of you who are familiar with circuit diagrams and things like this, we're talking about a very simple circuit, right? This is an alternating current source, in this case 60 hertz, 120 volts. Here's a capacitor. Just put it, a very simple circuit, an RCL circuit. Here's a capacitor. This stores charge. Here's an inductor. It's like a spring, but it's a magnetic spring. There's a magnetic field inside that kind of stores energy. Both of these store charge. This stores magnetic field, which also can be turned into electric field. Remember, electric field and magnetic field shake hands. So you can turn a magnetic energy into electric energy and vice versa. And then you have a resistor. This is where you dissipate the charge and create heat. Okay, this is a simple circuit, and you get that same power triangle. Okay, Don't worry about all this extra stuff. This is for people who care about it. If you want to know more about the power factor, you can go there. It's really kind of cute. They draw it out on like a little blackboard. You can see this is all hand drawn. But at any rate, why I have this here, outside of just giving those because I know I've got a lot of amateur radio operators in the in the room who probably build stuff. So you might actually appreciate it. If you don't, don't worry about it. But what I wanted to show was that, if you have a transformer that's creating heat, but in the power systems, granted, you have that. You have things that are taking the load and actually you're delivering real power to. These store the power, okay? They allow for the current to change, okay? But putting the charge holders and the magnetic field holders, putting these storage rings, so to speak, these storage facilities inside your circuit, then helps create what this phase angle is. Because they create reactive power. They're the power. These little storage things give and take. They give and take. This just burns power. This gives and takes. Okay? So it's these things in alternating currents systems that allow for the springiness and the ability to change and handle the varying loads of power. And it also, obviously, allows you to handle, to a great degree, geomagnetically induced currents, because suddenly you're getting more current in the system than you expected. Well, where do you think it's going to go? It's going to go here. Because the resistor is only going to, something that's drawing load is like, oh, I don't need, no, I'm full, thanks. I don't need a second helping of turkey. No, I'm good. Just what's on my plate is fine. That's what the resistor does. So where does that extra serving of turkey go? Or that extra serving of holiday food, right? Where does it go? It goes into here, into the storage, where reactive power is. So if you have a geomagnetically induced current, you expect your reactive powers to get bigger. Okay, but there's a problem with that, right? If you increase your reactive power, you make this wall larger in this triangle, what happens? Your phase angle must open up, right? You have to change things, or you have to close it. It all depends, right? So there becomes this dynamic that when geomagnetically induced currents are forced into a system, it's going to change this relationship. So here's where I tried to get playful, because we're going to talk a little bit about phase angle. And this literally will be the limit of my understanding thus far. I am going to continue diving in, but I will give you, I will be completely honest that this is not my forte, okay? But it's very interesting when you look at this. Now, in our current grid, in our power grids, we do not have voltage and current moving at the same time. So we talked about the sine waves, right? We talked about the waves going down and up and down and up. Well, believe it or not, in our current systems, or in our power systems, we do not have voltage and current going, up and down at the same, exactly the same time. And I should have put a T across this way because this time is moving this direction, right? So at this point in time, voltage is high, current is zero, or near, right? Current is zero. And as we move forward in time, voltage begins to decrease, current begins to go up. Okay, don't worry about the meeting necessarily. Pretty soon current goes to a maximum and voltage goes to zero. In this case, current continues to, voltage now is switching. It's gone to zero. Now it's reversing, because remember, this is alternating. This is an alternating current system. So now voltage going from positive is now going to a negative voltage, right? And current is now still positive, but going down to zero. At some point, depending upon the phase, this is what we're talking about defining as a phase angle, is the distance, the difference between these two, okay, in time. So as current then goes to zero and begins to go negative, while voltage was already at a peak, it's now coming back to zero. Do you see? So you've got this wave of positive, negative voltage, but it's not happening at the same time the current is ramping up and the current is ramping down. And the difference in time, that offset, can be set by the phase angle. Okay, the same phase angle that we just talked about in that triangle. Okay, this is how they're related. Okay, this is two different ways of looking at the same thing. Okay, so don't think that they're two totally different processes. This is just two different ways of representing the same thing. The other is a little bit more abstract and mathematical. This one is maybe a little bit more, um, hopefully, intuitive, as you'll see in a moment. Um, so for those of you who are not super familiar with voltage and current, let's talk a little bit about it. Especially when you're talking about voltage changing. Now, I'm just going to use analogies, real world analogies, and hopefully this is not, hopefully electrical engineers aren't going to freak out and go, oh, what are you doing? Voltage and current aren't the same thing. Okay, voltage is the potential to do something. So, for example, if you have a lake and it is dammed up, okay, right? Um, let me think. I got to be careful. Well, yeah, I can talk about it. If that lake is dammed up, then all of that water that's ready to go, okay, it has the potential to, you know, fall over and just really crash down and obviously, expend a lot of energy, right? If you were standing there and suddenly somebody made the dam evaporate and the wall of water hit you, you'd be like, oh my gosh, this is so powerful, right? That is a potential, the potential to do what we call potential to do work. In this case, drown you, smash you to smithereens, smash a town, downstream, right? That type of thing. That's the potential. It isn't doing anything, but it has the potential. That's what voltages are. Okay, so when you have a high voltage, you have a lot of potential to do a lot of damage, but the current has to be able to flow. In the case of a dammed up river, okay, or a dammed up lake, you have a lot of potential to do something, but you have no current because um, you're not being allowed to flow because the dam is stopping you. So current is how whether or not is basically, when you let that dam go, how big was the dam? How much did you let it go? How big, how wide was it? What was like the riverbed that you're flowing through? Okay, if it's a tiny little creek, well, you can let that go, but that's not going to be very big, so your current's going to be small. If it's the Mississippi, or some massive, or the Rhine, or some massive river, right? You're gonna that would be a signal of a lot of current. Okay, so in a sense, current can be kind of the analog is that current can be looked at as how big is your river, where voltage can be looked at as, maybe in a sense, how deep is your river. Okay, so like if you have just a tiny little river, it's not going to do anything. All right, and another way of looking at it, and I'll talk about that now, because as I'm going to put it in context with this, can also be the idea that what is flowing is not necessarily water, right? We know water flows really fast, really easily, right? If you were to pull that dam down and let that water flow, it right away, right? What if that were syrup, molasses, tar, right? You take the dam down and it goes, it just does, because the viscosity is so thick, it's just not really, eventually it will, but it's just not going to be moving that quickly. And that is another thing that has to do with current. So let's talk about those analogies in terms of this. Okay. So if you have voltage super high, but current zero, well, nothing's going to flow, but you just have a super high potential for that to flow, right? The only way that this voltage, this potential to do work, this potential to crash down into the valley below or something, that will only happen when you allow the riverbed to either open up or you remove the dam. Well, that can only happen once the current begins to rise. So as that current rises, you're taking advantage of that voltage. So at that point where you have current going positive and voltage going positive, they're both going in the same direction, you will have power being delivered. Okay, so you are letting that potential go. But notice that as this current is ramping up just a little bit, voltage is ramping down. Notice it's not exactly the entire amount, because if you had voltage and current both maxed out at the same time, boy, blah, you'd be able to deliver the whole load, right? But you can't, because as voltage is maxed out, current's like, nah, I'm not really feeling it. Nah, I'll let you go a little bit, but nah, not really. And then current goes, okay, yeah, I'm getting into it. I'm getting into it. And voltage is going, oh, I'm tired. I've had enough of this. So it begins to ramp down. So by the time current gets up to the max and goes, yeah, I'm really feeling it. Let's go, let's go. Voltage is going, right? Voltage is taking a nap. Says, nah, I'm done. And current's like, no, no, let's go, let's go. And voltage is like, no, I'm getting depressed. I'm feeling kind of blue. So, well, not really, it's red, but it's now moving in the opposite direction. Current's like, yeah, but no, let's go this way. And voltage is like, no, I want to go this way. No, no, let's go this way. No, I want to go this way. So you're not going to deliver any power at that point. So that's why they have this highlighted here, is that you're only delivering power when voltage and current are going in the same direction. Okay, so this is the power, this is the true power that you're delivering. But look how much more potential and opportunity you had. Okay, because you had actually higher voltage and higher current. They just weren't happening at the same time. So you couldn't deliver that much power. This is the true power. Okay, so this is how much power you're actually delivering. All of this stuff is almost like storage. Get it? This is where inductors and capacitors come in. This is where your reactive power is. Okay, so as this continues to drive, once current comes back down to zero and then begins to go negative, voltage is already at negative. It says, hey, you changed your mind. Good. Yeah, I told you we should go this way. Let's go this way. And current's like, fine, we'll start going this way. So then power gets delivered again. Why? Because voltage and current are going the same direction. But voltage is like, man, I waited for you for so long. I'm tired. I want to stop. I want to turn off. Current's like, no, no, I'm just getting into it, man. I'm just getting into it. Right? So it continues to deliver, but voltage keeps waning and flagging and flagging. Finally, when current's super excited, going, yeah, let's go this way, voltage is like, nah, I'm over it. I'm over it. Actually, you can say, I'm above it. I'm above it. I'm above it. Right? Anybody who knows that comedian. Because it's ready to go back this way again. Right? So once again, power delivery stops because current and voltage are not of the same mind. Reminds you of the northern and southern hemispheres of the sun sometimes, doesn't it? Sorry. At any rate, so when current maxes out and then voltage is back to zero, now voltage is going to go positive again. Okay, as voltage goes positive and begins to ramp up, current changes its mind and says, okay, I'll chase you, fine, right? And so we're back to the same thing we got there. So power gets delivered here, 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 poof, 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 poof. Alternating current, alternating power, right, in different phases. So this is time. So the way power is delivered in an alternating current system, really with this kind of out of phase, slightly shifted phase between the voltage and the current, allows for an apparent power that's much higher, even though the true power is only this much. Okay, and this becomes, depending upon how you change your phase angle, will change the amount of power delivered, and I'll talk about that in just a second. So let me just make sure as I run through the words here, okay? The phase angle is the difference in the phase between the voltage and the current in the AC circuit, okay? So the voltage and the current, right? And the phase angle occurs due to the inductive or capacitive elements in the circuit. The inductive element, that's the magnetic storage, right? What we saw is the little curly springy thing in that RCL schematic just a moment ago. I just go to it, for goodness sake. That's the inductor. Okay, this is how you store you can store electric current, because you in a magnetic field, if you change the magnetic field, you induce a current. Right? We already know that. That's how GICs are induced. Period. In a sense, we're kind of using the Earth's magnetic system as another L. Right? That's being induced into the power grids. Strangely enough. And we're using the bedrock as a C. So we're inducing more of these into the national power grids, not meaning to, but that's what happens with the Earth. Okay. So that's what the inductive is the L, the capacitive element is the C, and that's what allows the currents the apparent power to be higher than what's really truly delivered, right? Because I'm looking at this as intensity. I should label these axes. This is intensity, so higher voltage, higher current in this way. This is zero. That's what this line is all the way across is zero, and then this is intensity in the negative direction, right? So in an alternating current system, okay, the phase angle is defined by the time lag between the two, between voltage and current, okay? And this is showing how real power or true power is being delivered, okay? So, yeah, and so down here it's just saying when the power is only delivered when the current and the voltage are going the same direction. Obviously, they're going to be, if they're fighting each other, no power is going to be delivered. But you can imagine as you change the phase angle, the shape of this overlapping area is going to change, right? And this was what I did. Oop, there we go. Check that out. Is that cute? Oh, it's not moving quite as smoothly on your system as it on mine. On mine, it's really smooth. Here, it's a little bit laggy, but the reason why I did this was I'm talking about changing the phase angle, okay? So we're doing this, right? Look what happens to the power being delivered. So instead of it being that big yellow triangle, it becomes this smaller one. If I can get see where that is, becomes that, or even further in, right there, right? So you're getting less power delivered. And obviously, if that's the case, the amount of reactive power seems bigger. Because if this is the true power, then the reactive power is the stuff left over, okay? So you notice that as you change a phase angle, make it larger or smaller, you're going to be able to change the amount of power delivered. You're going to also change the amount of reactive power you have. If you were to shift this over far enough, you could make the voltage and current so out of phase that zero power is delivered, right? You could make this yellow thing disappear by shifting this all the way to there, so that when this is down, this is up, and and they meet at zero, and that goes down and that goes up, and meet at zero, that goes down, that goes up. That's what we're talking about of half wave failures, okay? You can make the whole system collapse by forcing that phase angle to open up till it becomes an open box. No power is delivered. Reactive power is the only thing the system has. Basically, you're forcing the capacitive and the inductive elements to take everything. And believe it or not, that's what happens with GICs, big ones. It forces this system to become more reactive. It forces reactive power to be the bigger part of the system. This can cause voltage collapse. This can cause cascade failures. Why does that happen? Well, look at our phase angles, right? See how the peak of this, when I move it over here, the peak of this is moving in a different location, right? It's moving over. Well, what's this? Here was the peak. Now the peak, what has happened? The peak has moved over, hasn't it? GICs move that peak, opens up that, changes that phase angle, forces the system to become more reactive, right? The reactive, so when a geomagnetic, so those of you who have heard me talk in the past, and I've kind of just washed over this point, I talked about systems, the magnetic, the national grids. When GICs occur, I say, well, what happens, you can't shut them down because they need more reactive power. Okay, I've talked about it and just kind of glazed over it. This is it. This is it. Okay, GICs force the inductive and the capacitive parts of the system to work harder, because suddenly you have all this current that nobody needs. Right? And it's like, well, what do we do with it? Well, we got to store it. Careful. This is an alternating current system, an RCL circuit. Well, you can't do that. If you try to store it all, you're done, right? Does this make sense to people? Do you guys, is this resonating? Resonating with anyone? Sorry for the frequency and wave joke. I hope that makes sense to people. Coke Machine says, oh yeah, okay, good. Yes. Oh, good. Well, I'll tell you something. If you can grasp this concept, even at this low level, I don't mean low, I just mean 50,000 foot, should say high level, right? Looking down from the 50,000 foot view. If you can understand this at this level, you will understand the issues of GICs far better than even a lot of space weather physicists do, because a lot of them don't understand the nitty-gritty when it comes to national grids. And this is part of the problem with being able to communicate to the utility companies and the people who work in the utility company consortiums, is that what they're looking at and the specifics of their systems are not only opaque to most of us, but they're so incredibly sensitive, right? And they're sensitive in a very non-intuitive way. Who would have thunk it, right? Who would have thought that by having a geomagnetically induced current, you're going to alter some of the fundamental springiness. You're going to alter the fundamental aspects of how an alternating current system like the national grid would work, because you're taking advantage of that springiness, that ability to react and change, right? And store power. But you'll overload it. Okay? This has been above my head for a minute or two. Oh, well, I'm sorry. I'm sorry, Sydney. Yeah, this is my first time trying to really explain reactive power, and it's not, and this is the problem, right? The problem is that that this stuff is non-trivial, right? When you start getting into the nuts and bolts of electricity and magnetism, we can't see this stuff, right? All we can do is diagram and make analogies, and analogies with a river flowing, water flowing and being dammed up, or the water suddenly turning. You can take a dam away, right? But if what you're holding back is molasses or tar, it's not going to, even when you take the dam away, it's going to take forever for it to begin to flow because it's so viscous. We can make those kinds of analogies, but it's they can only go so far, right? And that is, again, so in this case, we're taking a phenomena like space weather and Earth's magnetic system, which is already unbelievably convoluted and difficult to grasp. We're talking about how it induces currents in the rock beneath us. And then we have to talk about how that then couples in to a power system that in of itself is unbelievably complicated, right? From a non-expert perspective. So this is my first attempt at trying to give you at least some sense of how things are, how things can be so dramatically affected, and one of the main reasons why it's so difficult for us to solve this problem ultimately. Okay? No beer and foam analogy. Yeah. Well, good. I'm glad some people are getting it. Chris, you like the explanation. Kathy, you agree it's good. You've learned to respect the sine wave. Yes. Flutes, not trumpets. We don't like trumpets. The better the episode, the more likely I am to get a visit from an in-law. You got 4. Oh, I'm so sorry, Bark. Oh, that's funny. Yeah, well, hey, the gremlins were trying to get me earlier. They didn't want me to give a presentation today. So anyway, okay. Hopefully my little sliding sine wave here has been instructive. And in future, perhaps in future courses, I can dive more deeply in this for people who really want me to. But I am going to go on to talking a little bit more about the easier things. So that was probably the most technical aspect of the whole course. Now we're going to start moving on to effects. So those of you who are getting a migraine, you can relax now. The hard part's over. I did want to include this one thing from power system operation. Again, I did borrow a few slides just because I found it so interesting. and I wanted to kind of share with you. You know, so we're talking about this now. Hopefully, you guys are beginning to understand a little bit when we're talking about loss of reactive power support, possibly leading to instability in a power system collapse, especially if you start taking things offline, substations offline. Well, you're taking off the L's and the C's. You're taking off the ability of the power system to handle that reactive power, grab, right? It wants the system has to be able to be more reactive. And if you take substations and transformers and things like that offline, you're losing that capacity, which will make the grid fall faster. So this is one of the reasons why no matter what, we need to make sure that those automatic relay protections and fail safes don't just start shutting down the grid, which is part of the problem that happened in 1989. We weren't ready for it. We didn't know. And so a lot of the protective mechanisms began to shut the grid down because, oh, there's a problem here. Oh, there's a problem here. Let's shut this down. Let's shut that down. And it made the system that much more unstable because there was less reactive power available to store the GIC energy that was being brought in. Don't worry so much about this. For those of you who are interested in the type of transformers that have issues, there's multiple kinds, and power system operation actually talks about the multiple kinds. Don't worry about this, but you can see the springs, right? These are inductors, and it goes into a lot more detail than I would ever need, ever be all that interested in, unless you are someone who's interested in electrical engineering. But what I found interesting about this chart was that they were talking about, in this case, even the types of transformers that aren't grounded. Those transformers can't, they don't get directly impacted, or the generators don't get directly impacted, but the harmonic currents can actually enter the generators and cause mechanical vibrations in turbines. So if those generators, those power generators, are running through with turbines, or I forgot to put a thing on here, are running with turbines, the harmonic currents, turning a flute into a trumpet, can cause mechanical vibrations that could damage the actual turbines. Okay. And they're saying here, turbine mechanical vibration may increase during the presence of the harmonic rotor current caused by transformer saturation. So those harmonic currents can actually induce mechanical vibrations, which then can damage things, heat and damage. And the sad thing of that is the implications of that are really when it comes to our modernized grids, right? Do we have a clue yet how well the wind turbines that we're using now, that we're coupling with our smart grids, how well they're coupling into the national power grids, how well they can handle GICs? Are we going to end up having wind turbines and the rotors having mechanical issues? Can GICs impact those? I don't know. I did a cursory web search, and I'm seeing I'm not seeing any research done on that yet. But with the smart grids, when you have things like wind turbines and alternate forms of energy, there's all these new things that come in, and how do GICs couple into it? And right now, what I'm seeing a lot of people saying is that we're getting long transmission lines again with some of these smart grids, these new grids. And they're taking a lot of the capacitive elements out because they can actually cause more problems. So we have to be savvy, and thank goodness we have a lot of scientists in the loop stepping up to fight this and to understand more about the grids right now, because we could actually accidentally build back in susceptibility. And I'm hoping that as I continue doing a literature search, that I'm going to find this being addressed, where we're talking about not turbines from water generation, which is what we're talking about here, but in the smart grids, the new grids that are coming up, where we're suddenly harnessing a lot of the energy from these massive wind turbines. And are they all going to break, or are they going to heat up? What's going to happen? Don't know yet. But these are things that, GICs, it doesn't just affect transformers. And it's really this multifaceted issue with harmonic currents, how they can cause issues for us beyond what we already know. Um, I see. Good point, Joseph. Joseph, what did you say? Because they're not consistent speed like generator turbines. Oh, what are you talking about, Joseph? Those are coupled through inverters. Don't think that's possible. I hope you're right. I hope you're right. But I definitely would love to see some some work and some research on that excludes it, because good night if we don't pay attention to how the new infrastructures are being integrated into our system. Are we going to end up inducing issues that we hadn't really thought of from GICs? Everybody's so focused on transformers that it's not always just transformers. Okay, so the 1989 event was really, this superstorm was really what we call the standard candle. And it was a standard candle event for so many reasons. And this image here is kind of a nice little summary. I think you can get this in Wikipedia. Once again, I grabbed this slide from Power System Operation just because he had the information that's on this slide, which I'll talk about in a second. But the 1989 event was wonderful because I'm sorry, I have to, just in case any of my students are watching, I got to be careful. I got a test question I don't want to give away. But the interesting thing about the 1989 event is it kind of caught us with our pants down as a space weather a space weather operational society. It was before we had SOHO launched, and we were looking at space weather far more from a scientific and academic perspective back then than we do now. And so after this event, it wasn't just that we had the GICs that disrupted the James Bay, the Hydro-Quebec power grid and James Bay network. 9 million people, I think, 9 million, or no, 6 million people offline for 9 hours, 9 million people off for 6 hours. I can't remember. I think it was 6 million people offline for 9 hours. Remember, I'm dyslexic, so I have a tendency to switch stuff. But it closed the Toronto Stock Exchange. I mean, it was really surprising what it did. And as a matter of fact, it was the reason why the PJM consortium was created. And the NERC and the FERC really stepped up at that time to try to mitigate this stuff. So the standard candle event was a standard candle from the point of view of space weather operations, instrumentation, looking at the sun, but then also starting up this whole infrastructure down here on the ground. And really, when you look at the geomagnetic storms, some of the biggest ones that we've had in the recent times, the ones that were larger, both the 1859 event, where we're talking about deviations of the Earth's magnetic field, horizontal deviations, were massive. And I hope that's it. I hope that's not. You know what? This may be deviations not horizontally, but rather in DST. I should check that, because that looks familiar. That looks like the DST with a minus in front of it, obviously. But at any rate, just kind of gauging the different storms. We had, the granddaddy of all, the Carrington event in August of 1859. We had the 1903 event, you can see, not quite as large, but pretty big. Then the 1921 superstorm, a little bit less. The standard candle was the only one that happened really since the space age, right? And it was early in the space age. And so there are many events that were much larger, but it was the largest of the space age. Since then, we've had the Halloween events at minus 425 nanotesla. I think these are DSTs. That's what they look like. And then we've had the event in 2017, for example. We had a G4 storm not that long ago. So we've had other storms, but they're not as big. I think in the DST, or at least the deviation for that storm. And it wasn't DST, but the deviations that I'll show, the horizontal deviations, were like 350 or so nanotesla. So I apologize for not making sure that I knew where those numbers came from, if they come from DST or if they come from horizontal component movement. Not sure. I apologize. This is what happens when you try to put together something quickly. Give you all this extra information, and again, power system operation. The great chart, but need a little bit more context to know exactly what they're talking about. Obviously, not a space weather expert, right? But the event was a really good record of what was going on, and it was more information. As you can see from this chart, and this is why I have this up. This was taken. All of these different instruments were taken both in space and then also down on the ground, and also in the Earth's magnetic system. All of this stuff was available to us in 1989, whereas for some of these earlier events, we didn't have any of that, right? So it's kind of hard to do forensics when you don't have enough information. And really, this is about where where we can do really good forensics analysis and get a good idea. So we have a lot of analysis on this and storms that have happened since, and we'll talk a bit about that. So this is okay, yeah. So this is when I was going to talk about. I was actually going to play Kappeman's movie, and what I might do. Let's see, how long have we been going? 2 hours. Let me take a look and see where we are. I can't believe I'm going to have to do this class. I'm going to have another version of this class. We're going to have 4 installments of this. Where am I? I am. We're going to have 4 installments of this class. Crazy. Okay. What I will do, I think good. So I can get through that, and I can get through wet and dry transformers at least. Okay, because we'll talk about that after Kappeman stuff. What I will do is I will take my mic off. Sadly, I wished I could have the audio in there for you. I can try, but you'll have to bear with me because I have an audio system, but I don't think I can. YouTube doesn't let me change the microphone. That's the problem. Yeah, I can't do it, can I? YouTube is not very flexible. That once I start, I don't think it will let me do it. Once I start with a particular mic setting, I can't switch it like I can with a lot of other things. And it's not even letting me do it through OBS, and I'm not really sure why. So that's going to be a technical glitch I'm going to have to deal with. So what I'm going to do is I'll take my mic off, and I will have it play through this computer. But you can find that. You can find the Kappeman analysis, and I could go over it myself. But I like to let John talk, because you can find this analysis. It was done for IEEE. I'm not exactly sure why they decided to do it as a video, but there's a paper on it, and you'll hear him talk about it. This is analysis that was done clear back in 2008, but it's a really good analysis, and it really set the stage for what came afterwards. So I want you to be able to listen to it. And let me take my mic off so you can hear. So give me just a sec. You're probably hearing the mic all being all weird. All right, so let me play this for you.
They went from normal operating conditions to complete province-wide blackout in an elapsed time of 92 seconds. Hi, I'm John Kappeman. I'm a researcher, investigator in regards to space weather, especially their impacts on electric power grids. The animation I'm going to show you here is what I would call about 20 minutes of bad space weather that occurred during this March 1989 storm. And it kind of gives you a flavor for how large, how powerful, how fast and dynamic these geomagnetic storm space weather events could be. You can see here we're looking over North America at this time, and you're seeing the sudden appearance of a large region of geomagnetic field disturbance that is right now along the U.S.-Canada border.
What time period are we seeing here? We're seeing minutes go by in the upper left?
That's right. The clock, that I'm showing you there is the actual minutes of that day as this storm progressed. And you can see we started out at 7:40 UT, and within a matter of just a couple of minutes, we have a raging planetary storm occurring.
What are the colors actually indicating here? What are they showing us?
What we're showing you here is the level of disturbance in the Earth's magnetic field as observed at multiple ground stations across the planet.
So now let's look at what effect that had on the grid.
This is the same period of time as shown to you in the last animation of the planet. Now we're zooming in and looking at how that geomagnetic storm actually affected the U.S. and part of the Canadian power grid. Each of these red blocks that are shown here are significant power system impacts that were observed. And the most important of those was actually the province of Quebec. They experienced a complete blackout of their power grid due to this storm. They went from normal operating conditions to complete province-wide blackout in a elapsed time of 92 seconds. Virtually no time for them to even assess what was going wrong, let alone take any sort of meaningful human intervention actions to prevent that. The blue dots that are showing up are geomagnetic induced current flows that the simulation model is telling us would occur. And we're also showing you in vector formation the intensity and orientation of the geoelectric field that is created by the disturbance in the Earth's magnetic field. That disturbed magnetic field of the Earth produces a large-scale geoelectric field, which is what drives the GIC flow into the power grid and can disrupt the operation of the power grid. This storm raged for about 30 hours, and we had many other substorms or intensifications during that storm, and I've actually got a couple of animations that show you this event later in the day.
So this is the same day, March 13th, 1989.
That's right, yeah. And I believe this is about an hour of storm duration that I'm showing you here. And what you'll see is both an intensification of the westward electrojet, which extends across the upper part of North America well back into Europe, as well as an intensification of the eastward electrojet, which is well down into mid-latitude portions of North America at this time. As the storm went on, it actually increased in intensity and expanded equatorward. That's why you're seeing it now down over the central U.S., whereas before it was most intense along the U.S.-Canada border. What I'm also showing you again is some of the same features as before: geoelectric field, GIC by the blue balls that expand and contract depending on the surges of the geoelectric field. And you can see we had impacts that were observed all the way from the mid-Atlantic to the Pacific Northwest. And in fact, it was probably at this time that we came uncomfortably close to triggering a blackout that literally could have extended clear across the country. Yeah, these are photos from a transformer at a nuclear plant in New Jersey that during this portion of that storm that I just showed you experienced overheating in a matter of just a minute or so that was severe enough to permanently and completely damage this transformer. And you can see this is a very large transformer. These things are on the order of 200-ton shipping weight. The heating in these large high current windings, you can see how large they physically are, more than a human hand can wrap around them, was so intense that it not only burned away all the insulation on those windings, but actually started melting large strands of copper conductor. We had to have reach temperatures there in excess of 1,000 degrees C in those windings to have caused this sort of damage. So it was very impressive sort of event. So if you have a blackout that will also trigger wide-scale catastrophic damage to key apparatus like transformers, then you become very concerned about your ability to rapidly restore from that widespread blackout. It's always been our good fortune when we've had blackouts to be able to restore within a matter of a couple of days. If we have a big blackout caused by a space weather event, a much more intense space weather event, we may find that it is difficult, if not impossible, to restore. And it may take, weeks, months, perhaps years.
Thanks so much.
All right, thank you. Take care.
Okay. So hold on a sec, because I get my mic back being on me. Yeah, and I saw that. You're right. A small mixer, Greg, will fix the issue, and I do have a small mixer. My issue with today was that I expected very much to be able to just pipe it through my system, but I had a hardware failure, so I hadn't have it set up to switch between my my little Mackie over here. But yeah, in the future, that's what I may end up doing, is just have a backup set up that I can do that quickly. But I was taken a little bit by surprise today. So hopefully that wasn't too distorted. It definitely was not my favorite way of delivering that particular video. But I always let Kaplan talk for himself. I have an immense amount of respect for him. And he is still working away. He's still doing a lot of stuff. But this was really a landmark study that he did. And it really got a lot of people talking and got us to really pay attention. And as you can see, that again, that presentation was a long time ago. And so the fear mongering that happened at the end, saying, yes, it could take weeks, months, years to get it restored. Okay, right. But, the chances, the fact that that we're a bit more understanding, we have a better idea of how these things work, and that we have different protections in place. Back then, the relays systems just took everything offline. And so the cascade failure came much, much more rapidly. And the near complete cascade failure came much, much more rapidly than it otherwise should have. We've been a lot smarter. And, there are some national grids that boast, oh, we could ride it through anything. Yeah, I doubt it. Because, there's only, as we learned, right, there's only so much a grid can handle. There's only so much it can store. And so a GIC, you can imagine, again, the Earth's magnetic field is not that strong, but it is, it may only be the strength of a fridge magnet, but it's a fridge magnet the size of Earth. No grid can compete with that if we had a strong enough Carrington style event, So grids can boast all they want to keep people from panicking, but that type of honestly perfunctory or knee-jerk reaction is, I don't think that's the appropriate response either, because we shouldn't be complacent. Again, the sun is just beginning to wake up after multiple cycles of very low activity. We're going to see a lot more of the extreme events, maybe not Carrington class, but we're going to see more extreme events. So another 1989 or higher, that's still below a Carrington. We still could very easily see stuff like that. So one of the things I wanted to show you, moving beyond that, not that event, but moving beyond the Kaplan assessment, is how at both LASP and at NOAA, how a lot of this stuff is moving forward. As a matter of fact, Cameron, one of my ex-students, had done as an exercise for LASP and the University of Colorado. She had gone in and done a reanalysis of the grid based on some of the new technology that we have, where we actually, here's all the transmission lines, right? This is kind of similar to Kaplan, but now we have a lot more magnetotelluric assays that have been done. And she actually did a analysis where it shows the inducing of voltages, how many volts per kilometer are being induced in the lines during this storm. So I'm going to play this and you can actually see, we'll kind of chat through it, and you'll see how quickly it flickers. But where you get to at least a volt or beyond a volt, she only has this, but a volt per meter, which is quite large. And so let me just play it right here. So you can kind of see just with the transmission lines, you can start seeing where the non-conductive roots are, right? Because GICs want to flow up into the transmission lines where the ground can't conduct the electricity itself. So you see this, right? The eastern seaboard, you can tell, is quite susceptible. So is the northern part. Boom, there, look at that. Suddenly it lights up like a Christmas tree, right? And you're seeing a lot of the grid. Now, granted, they hadn't mapped all this because the assay at the time that this was being done, which was like 2 years ago now, the assay hadn't been done for this area. So we hadn't gotten the geology and the geophysics of the rock, of the bedrock assayed yet. So, you know, there are obviously some holes as of yet, but you can definitely see, notice it starts from, you know, the northern areas and then it moves south. And you see also, of course, where the geology is. So what you're seeing are essentially two impacts, right? You're seeing the effect of how space weather impacts Earth, right? And the bedrock, right? It always happens from high L shell to low L shell, okay? But you're also seeing now the effect of the geology and the geophysics of the region, the locales. Remember how I always talk about maybe in space weather is global, but at Earth, at the ground level, it's local, because you can no longer just look at space weather as being a CME coming at Earth, right? You have to look at the local geology. You have to look at the grid infrastructure, right? And you have to look at L shell. See how complicated things get real fast. And if you're not savvy with how you introduce, you know, the different assumptions that you make, you could drop something super important. And then that all of your analysis can be basically, you know, worthless. So that was that. Let me show you. Here's the electric field. So that was the grid. Here's the electric field induced essentially into the ground. So what we're looking at now was that at the time there were all these assay assessments, the magnetotelluric assays that were being done. These were all the locations in which those assays were being done. That's why you see it kind of like a peppercorn grid that's not exactly perfect. I mean, obviously, you know, some things are scooted over and stuff like that because there's things in the way. You can't get a perfect grid. But this is where they literally were all done. Now, I did talk to Jeff Love. This is he's one of the basically the lead scientist, the head guy who does this stuff at the USGS. I mean, this has been a passion project of his, I think possibly his entire career. He literally loves this, and I think it's fantastic because he is, I don't want to say he's not a lone warrior, but at the USGS, I mean, they just aren't funded for this kind of work as much as they really should be. So Jeff has made it he's just a crusader for this, and thank goodness he's there. So, you know, any fringe scientists who want to attack Jeff Love and the USGS, please stop. Just please stop. They get so little funding for this kind of work, and sometimes and there's been even times where the magnetometer network was going to be shut down. And we don't need people attacking scientists who are trying to get everybody else data, because when you turn people away from scientists who are trying to do good work, you end up hurting yourself. Right? We need these scientists to continue working. We need them to be respected, and we need people to advocate for them, not attack them simply because they work for a government agency. Please stop it. Anyway, that's just my beef here. Fringe science and mainstream science needs to work together, not against one another, or we'll never get this done. We'll never get the funding to get this done, and it's important work. So what we're looking at here, again, is the assays. And the reason why I'm bringing all this up about Jeff Love is that I went to him and I talked to him specifically while this was underway. And I said, I know this is a massive task. Obviously, you have to do every single one of these pits and measurements have been done hand by hand, right? By a small team of people who are totally underfunded. And I said, when you did the magnetotelluric assays, did you exclude times when there are solar storms? Okay. I said, did you do that? He said, no, we couldn't afford to. We had to do it when it was happening. So if the Earth's magnetic system was wiggling while we were doing our assays, I said, how bad would it throw your assay off? He said, yes, it will. So granted, this is not as good as it could be, right? Because they just don't have the funding to be that critical. So it's the best they can do. But understand that this is still very much experimental, and there are errors, right? But it's the best they can do with the funding that they have. So take a look again, and you'll see it even better than you did with the transmission lines. You'll see, whoops, let me make it big. You'll see the how it works. You'll see the effect, especially latitude dependence. You'll see the effect really beginning to show. So you definitely see it, of course, with the geology, right? Especially in the northern part, northern tier at the American-Canadian border near the lakes. But you also see it on the seaboard, but you definitely see it going from north to south, right? It lights up all the north before it lights up the south. And that is the effect of L shell. But look at that thing lighting up like a Christmas tree for 1989. So these were the voltages being induced. Okay, the electric fields being induced in the ground. And I'll let that play for just a short bit. But you can see there were actual 3 independent hits. Oops, and I'm standing in the way, sorry. I think there's one more little something, and then it'll stop. I think it stops at the 20th. Yeah, there's a little bit of lit up. There you go. All right, that's probably good enough. Now, one more I want to show, and this shows it better than even that. We're now going to look at a slightly different plot. This is now the magnetic field, right? So what we were seeing were the currents driven into the ground. Now we're going to take a look at the horizontal perturbations of the Earth's magnetic field dancing, okay? So what you're going to see are arrows, right? And in this case, you're going to see arrows that not only change color, but lengthen. So small magnetic perturbations, okay, left, right, up, down, north, south, east, west, right, will be in black. As they get larger, about 100 nanotesla, you start seeing them in purple. If they're 1,000 nanotesla, you'll see them in white. Okay, so the same event, but we're moving further out because now we're going to look at this. Notice that the plot is spherical, right? I mean, in other words, you're seeing the lines that are curved, right? You can look at these to some degree as different L shells. Don't count them necessarily, but you can see how you go from high L shells to low L shells, right? So out here, right, is where you're going to see a lot of the electrojet. And as remember, as Kappeman showed, the electrojet, you had the western electrojet up here, you had the eastward electrojet come down below, okay? All of that, you're going to see what it does to the magnetic field. And the magnetic field is going to look like Austin Powers going like this here pretty quick. Okay, it's pretty cool. But you'll definitely watch waves come in, and you'll see it from high to low, right, from north to south. And imagine in the southern hemisphere, any of you coming in watching from down under, it goes from south or from the south to north, right? Because it's the opposite as it is here. But it always goes from the poles on down. So check this out. This is really impressive. At least to me it is. So you can see those wiggles. You can even see where the perturbations begin and where they dip down, especially once the storm really hits. But this gives you an idea of how much that Earth's magnetic system is really wiggling, even at the foot points of the magnetic field as it hits the ground, as it impacts the ground. Remember, these are just north, south, east, west, horizontal perturbations of the Earth's magnetic system. They are not, there you go, here we go. Right, these are all parallel to the ground. But you see how it moves? And so all of this movement, anytime you have a magnetic field that's moving, you're going to induce currents. So now you really see not so much the geology, but the geomagnetic variability, okay? So this is what's happening from a space weather perspective, and then once you have the infrastructure on the ground, then you have to look at how the ground itself is different, and the geology of the ground and how well it conducts the electricity that this magnetic field is inducing. Right? And then that then transmits into the power lines and impacts the transformers. And then the transformers are what we'll talk about next. Okay. Interesting? Does it kind of give you a better appreciation for the complexity of the problem? Hopefully. Yeah, no. I'm going to buy up tinfoil. No, not the kind of response I was hoping for. I'm not trying to scare people. What I'm trying to do is give you an understanding of why the research in this area is slow, but how incredibly important it is, and also how multifaceted it is, in that you can't just turn around and say, shut it all down. You can't just turn around and say, this is the transformer, or this is the area that things are going to go to hell in a handbasket. There's so many different things that have to be put together in a very thoughtful package to be able to make assessments. And so when you see a solar wind or a space weather event, a big Carrington class event, even if you see a Carrington class event coming toward Earth, do not assume, you cannot assume that it's going to be Armageddon, that it means Armageddon for Earth, right? It all depends upon how it hits, what it looks like at the solar wind, how the grid responds, what time of day it is, right? What the load is on the transformers, how busy is the grid system, how old are the transformers that are being hit. I mean, it's just, there's, what is the geology of the area involved? Goodness. What is the duration that this storm is going to last? There are just so many factors, right? Yeah, from North Dakota to Louisiana, yikes, right. And that's the thing, is that with the big geomagnetic storms, the solar event, the space weather phenomena hits Earth and begins to peel back the Earth's magnetic system to get from high L shell down to low L shell. Once it gets down to, peels enough flux back to get down to lower L shells, that's when you're seeing on the ground all the effects going from north to south, from high latitude to low latitude. That's why the auroral electrojets come down so low. Is the Earth's magnetic system, the flux is getting peeled back, that auroral oval is opening, right? As I always talk about the polar cap, you're pulling the cap down further and further over your head. If I'm Earth, I'm pulling a little teeny tiny beanie cap all the way down over my eyes, right? You have to open it up, the Earth's magnetic system. You have to open it up to be able to dissipate all that energy. And so that's what the Earth's magnetic system is doing when it's doing the Austin Powers dance, right? It's dissipating energy. And some of that energy gets induced into the ground, right? And then voila, we have a alternating current system power grid that can handle. It can store a little extra power, right? And so it does. But that affects the power, its ability to deliver power, right? Because of the way it's constructed. So everything, one thing couples into the other, and you see, and it becomes this kind of thing where, in order to answer the question of will it impact the power grid, you literally have to walk backwards very, very carefully to the source, because there's just so many steps and so many things that are involved. Okay. Amazing we have gotten by so well for so long. Well, what made it lucky, to be totally honest, is we have had 2 to 2.5 cycles, solar cycles worth of very sleepy sun. If we had just this, if cycle 24, which was the cycle that we just had in the just this last one, right, the one that peaked at 2015, if we had that cycle, instead of being as low level as it was, if we had cycle 19, which was a big cycle back in the 1980s. If we had had that cycle now, we would not have fared so well. But the nice thing is, the fact that we've had a sleepy star over the last 2 cycles has given us the opportunity to learn through little tiny problems, right? Small power outages instead of the massive ones. So the thing is that Kaplan was talking about 2008, the mindset back in 2008, which was, oh my gosh, we're going to get caught with our pants down. But we've now had another decade to kind of work the problem, more than a decade, almost 15 years, a cycle and a half. And thank goodness during that cycle and a half, the sun has been, I'll give you guys a break. I'll cut you a break. It's like playing hide and go seek. I'll give you a head start. Go ahead. I'll count. The sun's going 1, 2, 3. You know what I mean? We've been lucky. The sun has been a benevolent star instead of an angry star. But as we're beginning to see, and if Scott McIntosh and the NCAR crew are correct, the sun's done counting. The sun's like, ready or not, here I come. So we may be in for that kind of, thing here soon. We'll see. So back then, Kaplan did this study, and this is from his work, of all the extremely high voltage transformers. That's what he's talking about, EHVs, having to deal with something that's at the level of a 4,800 nanotesla per minute geomagnetic field. Now, granted, that's not per second. So this is sadly, when you get into this field, you have to translate all sorts of different things. So I don't, take this number with kind of just a grain of salt, because you're probably not going to see too many numbers that are that you can translate this to, at least in the presentations or in the analyses that I see now. Things are done per second, things are done per kilometer, things are done per phase, but I don't really see nanotesla per minute changes being talked about very much. But again, this analysis was done back in 2008. And as you can see, there's quite a few transformers, at least in the United States, that have some level of susceptibility, okay? And, that has changed. Sadly, a lot of these transformers are older, and we'll talk about the issues with that in a second. But we've gotten a lot smarter about trying to tell how the health of a transformer, and I will be able to get into that here in a minute. Before I do that, just for edification, I'm not going to go into this in any great detail, but since most of our viewers, and myself included, are in the continental United States, it's good to know that our electric grid really is split into 3 parts. Texas, sadly, is completely isolated. And if anybody who lives in the Texas area, oh my goodness, with what happened, a winter or so ago, and the freezing, and like there were 4 minutes from collapse and all of that stuff. Could you imagine? One of my good friends, Mike Cook, who actually lives in Texas right now and was part of the, just recently left the space radiation analysis group at Johnson Space Center, and took a job with MITRE. Actually, he moved on. He's moving up in the world, but he lives in Texas, and he said, could you imagine if there was a geomagnetically induced current, a big solar storm happening at the same time that Texas was dealing with it? And I went, oh my goodness, no, because Texas is so isolated. Their grid is not, it's only connected by just a few transmission lines here to this side, to the eastern side. The western side is also basically its own thing with just a few interconnections to the east, right? So there are susceptibilities built in, because remember, we were talking about reactive power and how you need to make sure all the substations stay up as much as possible. And if you have a substation that with a transformer that's sick or overloaded and really has to be shut down, and we'll talk about that in a sec, how they're able to tell, or at least some of the ways that they're trying to learn how to tell. If you have that, then you better pray you've got a lot of other transformers that can handle that excess load. Well, obviously, if you have isolated things where there's not strong interconnections between the different parts of the power grid, you limit yourself, right? So these are things that they're looking into these types of inherent weaknesses, because obviously these grids were not designed with that in mind. They didn't know that these types of things could happen, right? So this is something that and plus I think also the issue here, maybe this is where some of the largest high power, high voltage transmission lines are. And so they're long and unbroken. Yeah, as a matter of fact, this even says linked by high voltage DC ties. So lots of these are really high voltage DC ties that can be GIC susceptible. Okay. But I really worry about Texas right now, especially with what's happened with their grid. Luckily, geographically, where are they located? Right? Way down south. Thank goodness for that, because when we talk about the geomagnetically induced aspects, right, we're not talking about geology. We're talking about geomagnetism, right? We're talking about the Earth's magnetic system. This is high L shells up here, low L shells down here. Texas is protected to a great degree, right? Only a really big storm is going to impact them. Okay. So as I've been saying over and over again, research into geomagnetically induced currents is a major undertaking. Okay, and I found this from this was really nice. It's summarized from Thomson in Advances of Space Research, but this is back in 2010. But I thought this was a really good thing because it kind of sets the stage for where we are now. So back in 2010, okay, and this was actually presented at the NERC. Back in 2010, these were the major knowns in GIC research, right? We knew about solar storms. We knew that they caused them. Yay, we've known that for quite some time, okay? And that it happens at solar max and the descending phase of the solar cycle. Because remember, the descending phase of the solar cycle is when we get those big trans-equatorial coronal holes with lots of fast solar wind that just rings Earth like a bell every 27 days, because these coronal holes they survive their rotation around, the backside, the far side passage around the sun, and come back every 27 days. Hello, Dolly. And then they go back and then come back. Hello, Dolly. And satellite operators hate that too, right? Because it really energizes those radiation belts. So it's a real problem for health and safety of satellites. But it's also not a fun time for the national grids, because we get just constant, transformers every 27 days are having to deal with it. Remember, GICs happen with every geomagnetic storm. It's just that most of the time, our grid can handle that variability, can store that. So GICs really aren't that much of a problem. It's only when it's a G2 or higher and it's sustained, okay? Because then you take longer time to heat and the heating gets out of control, and you'll see what happens. Well, we'll talk, like I said, I'll talk about it. So, okay, so we knew this, all right? GICs are larger in countries and regions where the geology is generally more resistive, and a multi-layered and laterally varying ground conductivity model gives better prediction than a simple homogeneous view of Earth. Of course, right? Where the bedrock doesn't like to let stuff flow, let electricity flow, well, the electricity is going to be more interested in getting into, the transmission lines, right? What would you rather be stuck in, a traffic jam or driving on the Autobahn, right? So you're more motivated to look for alternate routes when you're stuck, right? Just like with human beings in traffic. So we knew that the magnetospheric and ionospheric currents that drive GICs are different at different latitudes, right? And the dominant cause of GICs and power grids is the time rate of change of the Earth's magnetic field. D by dt, right? That's what we call it, dBdt, the change, the rate of change of the magnetic field vector, or in this case, horizontal magnetic field, parallel to the ground over time, right? So it's the Austin Powers, right? The dance, that's what we're talking about. The time rate of change that the magnetic field can flip around, that creates an electric current, or an electric field. And that electric field then causes the bedrock and causes the electrons in the bedrock to want to move, shake, rattle, and roll. And they want to get unstuck, right? So then in industry, so that was the science part. We got that. Back in 2010, we were pretty good on that, okay? In the industry, so now we're looking at the power grid side, right? We're seeing that it affects at all latitudes and can affect many transformers simultaneously, right? So this is just 2 years after Kaplan did his analysis, Okay. And we're seeing it, oh my goodness, it's regional and continental. Huge networks, right? And that was the prevailing theory, which is part of what motivated all of these doom and gloom assessments that we're going to be thrown to the dark ages. Oh Lord, okay. Now, granted, we're going in a little bit more in depth here. Series capacitors and transmission may interrupt GIC flow. This is where saying, okay, well, let's just not have 400 miles of unbroken transmission lines. Let's just make it smaller. Okay, great. And you could do that. But remember, capacitors, both capacitors and inductors, they are magnets for reactive power, right? So it may actually increase the reactive power demands, because the more capacitors you put in a circuit, and more along these transmission lines, the more reactive power you can possibly store, which will bring you faster to collapse potentially if you turn the entire circuit into a reactive power, behemoth, right? Because then you can't deliver any power. That will cause voltage failure. So that isn't it. Just a simple solution like that is not necessarily the way to do it. Okay. And now this was a new one. Transformer dissolved gas analysis, we will talk about this, identifies these GIC initiated damage before the transformer fails. Okay. And this is especially true if the rate of gassing simultaneously increases in widely separated transformers across a network. So when they hadn't done this before, this is what they started thinking. And I love that they're doing this, because this also helps them identify wet transformers versus dry transformers, which may be one of the biggest problems that we have. And I'll tell you why in just a sec. But we didn't do this before. Okay. One of the biggest issues about transformers is that they get hot, right? Just doing the work that they do, they get hot. Well, you don't want to cool a transformer with water, right? Or even antifreeze, because they get really hot. So what you need is some liquid that can handle super high temperatures without boiling. Well, what's a good one? Oil. Yes, oil. Oil can go to hundreds, if not maybe potentially thousands of degrees, depending upon the kind of oil, before it breaks down. That's one of the reasons why it's used as a coolant in car engines and right in mechanical car engines. It can really handle super high temperatures and not break down. What is the problem with oil? Well, it's flammable, and it can burn, and when it begins to break down, it begins to boil. It can boil out flammable gases, which then combust and burn even easier. They don't just burn, they explode. You really want that inside a transformer. What does a transformer do? Well, it allows electricity to flow without sparking. But what happens when it begins to break down? Well, it sparks. What's spark? Like a little mini fire. You mean like a match to oil? Yeah. What's the oil again? Flammable. What's a spark do? Lights it. What do the gases inside the oil do? Explode. Do you see the perfect, do you see like the perfect storm waiting to happen? Yes, transformers are potential bombs. Should I say that again? Transformers, especially high voltage transformers, are potential bombs. Sad, isn't it, right? That the thing that helps us the most to keep these transformers functioning, when they malfunction in a spectacular fashion. But this is why this is so important. Okay. So what is it? Dissolved gas analysis. What I call the dipstick of transformer health and safety. This is something that I maybe this has been done, and if any of you actually are from the power industry or know this stuff, maybe Fenton, maybe Roger Fenton, you're on. Let me know, how long has this been done? Because I have only come across it recently, but I'm just thrilled by it. So oil, and hopefully you can read this stuff. I'm hoping you can read this. The oil that we typically use in these transformers, right, can break down. And you can see here, acetylene, ethylene, ethane, methane, and hydrogen. Okay. All of these gases, as far as I know, right? You remember acetylene lamps? They stopped using acetylene. Why? Well, because it explodes pretty easily. But they were used for acetylene, for lighting, right? All of these are quite flammable. Hydrogen, you think? Hindenburg, anybody? So sadly, these are the kind of gases that can be liberated as you heat transformer oil. And you start heating it to breakdown temperatures. Not normal operating temperatures, but breakdown temperatures, okay? GICs, as we saw with the harmonic currents, cause transformers to heat up, right? It's causing a lot more current than we wanted. They're not supposed to be working at that range. They're not supposed to be trumpets. They're supposed to be flutes. You turn a flute into a trumpet, it's going to get mad and it's going to get angry and it's going to get hot. Okay. So as and this happens, I mean, it happens normal, operation of a transformer, right? I mean, how many times have you picked up a transformer when you're after you've plugged in your phone, right? And you feel the transformer, the wall wart or the line lump, and you feel it and it's warm. Yeah, that's a transformer, right? So it's a low-level transformer. Well, same thing happens with the big ones. Just by working, they get warm. So they need to be cooled. So oil is a typical coolant for them. And if you can see this line right here, this line is talking about normal operating temperatures, about 65 degrees C, okay, at least according to this plot. Now, what we're going to talk about here in just a second is temperature goes up this way, okay? And so what we're looking at this plot, on this plot, is it's a cartoon. It's not, there's a lot of qualitative aspect of this, but it's a cartoon you can find pretty much anywhere. We're talking about hydrogen being created. We're talking about methane being created. We're talking about ethane, ethylene, acetylene being created. They're all color-coded. And what we're looking at are different temperatures at which they are created and to some degree how rapidly they're being created. How rapidly they're being created is drawn by how wide this swath is at any one particular temperature, right? The vertical lines are temperature. So at 65 degrees, which is this first vertical line, okay, no gases are being created, right? It's normal operation. But let's jump forward to about 150 degrees C. That's the edge of this box, okay? This is where you start seeing oil beginning to break down, okay? You start seeing hydrogen beginning to form, be liberated out of the oil. You start seeing methane being liberated out of the oil, okay? But that's about it. As temperature continues to go up, now we're at 300 C. Isn't that right? Is that 200? Sorry, 200 C. Okay. More hydrogen, you can see that is beginning to widen. And you can see methane is also widening. So now you have methane and hydrogen, two flammable gases in the oil. Lovely, right? They're bubbling around in there. So you've got bubbles, right, in your oil. Really teeny tiny bubbles, but basically your oil is getting the bends in a sense. Not really, but kind of. Okay. And as you move beyond, this is now what? Oh, that's 200 C. Now we're going to move to 250 C. At about 250 degrees Celsius, assuming the GIC is continuing. Do you see why? You see why duration of a solar storm begins to matter? Because it takes time to heat the oil, right? Typically. I mean, especially if a solar storm is weak. If it stays sustained at a certain level, but it continues, then you can slowly heat the oil up. Obviously, if it's a big solar storm, you're going to heat it up real fast, right? And there's also the EMP aspect of it that's a problem. But and that's a slightly different phenomenon. But let's talk about a solar storm that's causing a GIC that can be handled, but it's causing that transformer to overheat. The longer it overheats, the higher the temperature gets, right? Typically, if it can't find some steady state way of burning it off. So we're assuming it's not in equilibrium. So now at 250 degrees C, now you're going to start getting ethane in the oil, okay? And again, and you're still ramping up production of these other gases, right? As you can see, at some point between 250 and 300 degrees C, which is between here and here, you begin to ramp down the production of methane. And I don't know if that's because methane has been all liberated out, or it's just preferentially being created, ethane is being created instead, okay, is being liberated out instead. And so all of the carbons are going to ethane, right? But methane production begins to go down. But now you've got 3 different flammable gases dissolved as you continue to heat and heat and heat. I'm not going to go through all of these. 350, then you get acetylene. That's when acetylene comes in. And at, not acetylene, ethylene comes in. And then at about 500 degrees C is when acetylene comes in. Very, very, this has been outlawed in terms of at least lighting a lamp gas because it was so explosive. And as you can see, once you get up to, my goodness, 700 degrees C or so, the amount of acetylene that you start creating is insane, right? But you've got a lot of gases now dissolved. So the cool thing, pardon my pun, is that if you can assay the molecular constituency inside your oil and discover the gases, which is possible, right? There's lots of techniques, lots of chemical techniques that allow you to do that. If you can do that and sample that oil, then you have an idea of where you are in terms of how close you are to complete breakdown. And that's kind of what the Duval triangle is talking about. And I'm not going to go through this, don't worry about it. But you're talking about here, you've got, this is acetylene, okay, on this one, C2H2. This is acetylene, and this percentage of the oil that has acetylene in it, right? You can see it actually goes from 20% all the way up. Here is CH4, this is methane, right? And it goes again from low levels to high levels. And then this one, what is this? This is C2, is this C2H4? Yeah, this is ethylene. So, and again, you go from low percentages to high percentages. But you can see this triangle is covered, right? It's color-coded. And so there's all these different areas that if you have the percentage of methane, acetylene, and ethylene in a particular grouping. So you have, in this case, you have 70% methane. Let me do it in here. 70% methane, but only about 50% acetylene, and then only about 25 to 30% ethylene. Then you're in the D1 level, right? Well, what is D1? Whoops. What does D1 mean? D1 means discharges of low energy. Ooh, ouch. Little sparks, mini sparks. Oh boy. Okay. If you are in, D2, then you're going to get discharges of higher energy. Oh, bigger sparks. Yikes. Right? So you have these fault indications that are basically assayed by understanding what this means and how the chemistry inside of oil, how it breaks down slowly but surely as a transformer is heated. So it can give you an idea of what the health and safety is of any particular transformer. Now, this is a dry transformer, okay? A lot of the new transformers are the big ones. We're talking the big ones, right? The hundreds of kilovolts, right? If not thousands of kilovolts, the big guys. The ones that Kappeman was talking about in the, and I think it's not even the biggest ones. I think the ones that we really, really worry about. I think it's, I'm trying to remember, Roger, if it's, did you tell me 750 kilovolt? I forget. My apologies. I can look that up. I knew it yesterday, and I'm too much stuff in my head. It keeps pushing other stuff out. So, yeah, I wish I could remember that exactly. I'm afraid to say, but I think it's 750. Anyway, these are dry transformers. Okay, these are new ones, and the neat thing about the new ones is that they've got a lot of these tools and assays that and systems that are either set up. Hopefully they're wired, but they're the biggest thing that we fight now is that a lot of the new transformers have all these things built in, the tools built in, but the infrastructure that they're being placed in is so old that, it's like, you need a Wi-Fi connection? Will the telephone do? No, we need a Wi-Fi. How about a modem? No, can you have Ethernet? So now we're fighting having these really brand new shiny things placed into these operating locations, and yet they're too brand new, that the infrastructure in which they're placed in is not capable of handling all their capabilities. So we're not taking advantage of some of these tool sets that we have, because more modernization needs to occur in areas that aren't quite so, pardon my language, sexy, right? I mean, everybody loves to have brand new shiny transformer. That's the big new shiny thing. Nobody wants to pay for the cabling and the Wi-Fi internet that powers the shiny thing. They want to put their money into the shiny thing, right? It's the same thing as someone buying a necklace. You buy a necklace not so much for the chain, but for the pretty pendant that's on it. Everybody wants to look at the pendant, not the chain. But the chain is critical. Without the chain, the pendant doesn't hang, right? It falls off. So that is part of the issue that we have with power systems, is that the infrastructure needs to be modernized as well as the transformers. And these are great tools, but this is for a dry transformer. We can use the same kind of mechanisms and technologies and dipstick of health assays on wet transformers. The problem is the old transformers. The problem is these old transformers have one other problem, one other issue, and some people have heard me talk about them before. Do you see water anywhere on this list? No. And for a good reason, right? You shouldn't have water in a transformer, right? Normal operating temperature is at 65 degrees C. Yeah, water can live, right? But once you get to 100, water boils, right? So water would boil in between these two lines, right? Right. The issue that we have with wet transformers, with old transformers, is that a lot of them are parked outside. Well, outside, there's condensation. Condensation has a tendency to get inside electronics. Anybody who has an amateur radio rig knows that. Why is there water in my cables? How do I get the water out, right? Well, water gets inside transformers too. If they're new, their gaskets and their water seals are great, right? Keeps water out. If they're old, well, not so well. So what happens? Water gets inside the oil, right? It goes in through all the gaskets, inside all the fixtures, and manages to get inside the oil. Water doesn't mix with oil, right? So it forms little bubbles inside, little liquid water bubbles. But as it floats around in there, it sees the insulation. The insulation is paper. So all those windings that Kappeman was showing, they're all insulated by paper. There's literally paper wrapped around. Well, water sees that paper and adheres to the paper. Okay, so now you've got wet paper inside oil. How do you deal with that? What happens? What would happen? Now remember what insulation does. Insulation is there to protect the windings. So you've got lots of windings really close together, right? And they can't spark, right? They would normally short out. Remember, electricity is always looking to find the path of least resistance. It's always looking for the short. So the only thing keeping the windings that have electricity flowing in either opposite directions or with a potential difference between them, the only thing that stops them is this paper insulation. Okay, and now it's a wet paper insulation. Okay, but it's still doing okay. It's still doing its job. The problem happens when you go from normal operating temperature to GIC operating temperature, where you begin to exceed 100 degrees. What does water do when you reach 100 degrees? Oil doesn't care, but what does the water do? Boils out of the paper, right? It liberates, becomes gas or steam, right? What do you think that does to the insulation? Think it might shred it? If that's your guess, you're right on. So now you have wet paper in a wet transformer at 100 degrees C, and it shreds the insulation. Uh-oh. What do you think electricity does now that it sees a clear path between itself and the nearest winding? Arcs, right? Discharges, right? In In this environment, which one of these gases do you want to light up first? Okay. That is the problem with old transformers. They work just fine. So power grids are going to use them to failure. I get that, right? There is no money to replace them quickly just because they have water in them. Okay. Can you take them offline to drain them and refill them? Well, why? Because you're just going to get water in there tomorrow, right? I mean, it's not really a workable thing. Besides, they've got to work all the time. It's kind of hard to take them offline, transformers like that. But it does cause the bomb issue to become a little bit more important, or a lot of bit more important, right? Because now you're not talking about thermal breakdown and dark discharges when you get up to hundreds of degrees C, right? We're talking here, this one's showing 800. Okay. This is like 500. This is 300. Okay. We're talking way out here, just barely above normal operating conditions. It takes a big GIC to push the temperatures out here. But how big of a GIC do you think it takes to go here? Not much. So that is the problem that I'm not seeing considered enough. This is the problem that Roger Fenton let me know about, and he's been working in the industry, the power industry, for 40 years, I think. I haven't done a lot of research to see if there's a lot of open source papers on wet transformers, but it's well known in the industry. But it's not something that a lot of people want to address because it's hard to capture that, and it's hard to know. But it is a significant problem. So that is really the issue when it comes to transformers and faults. We do have the ability, especially with the newer ones, to keep them safe and know when we have to take them offline, or if they can ride out a storm, no problem. But the wet ones, they're really crippled. These are the ones that need to be taken consideration first, right? And so as we modernize the grid, that's what they're doing. They're taking into consideration the weak transformers, probably the older ones, or the ones that have other issues, the ones at higher latitudes, right? They're taking into consideration all of these different things. Any questions on that? By the way, here's a paper by Jeff Golars that I got a lot of this stuff from. Okay. Anybody have questions on that? Or does that make sense? Oh, SpaceX, yeah. Yeah, SpaceX. The sad thing is that when they launch into a solar storm, God, did they lose more? God, I hope not. When they launch into a solar storm, it makes you wonder if he says, okay, well, if I launch and they make it, it's great. If I wait, though, how much money do I spend burning on the pad in wait mode? Right? I mean, there's obviously a cost analysis and a trade analysis. And I don't really even know, once the rocket is sitting there ready to be fueled and everything's in place, they've got to launch to that orbit. It's not like on the fly they can say, oh, we'll just up the altitude by, 100 kilometers. You can't really do that. I mean, you can't do that on the fly. So, I mean, there's a lot of things that go into that trade space, but I do think that's going to be part of the part of the future, is that we're going to have to be more versatile in terms of dealing with space weather and knowing that we can reduce the cost of just either waiting on the launch pad or being able to change our the ConOps on the fly. That's going to take some rethinking of how we do things. But space weather is becoming a bigger player in a lot of areas. And if the sun continues ramping up this solar cycle, to be much bigger contender than 23 or 24, cycle 23 or cycle 24 was, then, people are going to be scratching their heads and going, wow, the old, the old stuff that the way we used to do it ain't the way we can do it now. This isn't your grandmother's solar cycle. And they have to understand that. So it's a really neat time to be a space meteorologist, if you want to call it that, because space weather is becoming really the weather of the 21st century in so many ways. It's kind of neat. Which agencies' debts make the decisions by state? Which agencies make which decisions for the grid? Ooh, the consortiums do, right? A lot of these consortiums are the utilities are private. Not all of them are owned. In the UK, they're owned. The national grid is owned, but there's a lot of consortiums here that have private utilities. So that's why you need a NERC and a FERC. You need the federal, but you also need you need private industry as well connected to it. It's very complicated. Okay. They would have to remove satellites from the payload to go higher. I don't even think they could do that, though. I mean, because it has everything to do with the amount of fuel that they put in and what they've cleared, the region for. I mean, there's all sorts of permissions and infrastructure and red tape. Let me just say that red tape that they have to go through to make sure that they're going to park the spacecraft, even in their transition, their transfer orbits. They have to make sure that they're going to be launching in an area that has been cleared and has been green lighted by by the government agencies in charge. So yeah, this isn't, you like that? Understood. Yeah, this isn't your grandmother's solar cycle. So okay. Could copper pipes pointed south-southeast with dry ice at their base draw warm air? Oh my goodness, I have no idea. That's not something I'm going to even tackle. I would think I would think that there's too many losses for that to be even a workable idea. Okay. Let's see, those kinds of transformers are super expensive and you can't buy them at Best Buy. Yeah, they do. It's true. And not just that, as I said earlier in this stream, they also it's not even just making them, right? Once you get them, that's great, wonderful. But even if you had them at the ready standing by, and now you need to transport them to their destination, they're insanely difficult to transport because most roads are not designed to handle those things. They're so massive that there have been times where they've literally had to dismantle street lights. I mean, I've watched some movies that were just almost, they would be funny if they weren't so tragic, that they literally had to dismantle street lights to be able to get these things to pass under them because they're too tall. And they don't always know, because streets, are not designed to pass these things. They're never made with these things in mind. So when these oftentimes these the plots, the diagrams of which streets to go and the path it has to take, the vehicle has to take to get these big loads to their destination can be very convoluted because there's only certain ways they can go. And that is not something that's plotted out very often. So, as infrastructure changes, old courses that worked before may not work now. So these things, they're very unwieldy. It's not just a matter of making them and then using a sky crane and dropping them off. I mean, we're not going to use Amazon drone to fly them over and land them. These things are insanely difficult to just even transport. And that is a huge part of the time it takes to get them to where they need to be and then installed, right? Let alone functioning. So yeah, we don't want these things to go down, which is part of the reason why they're taking such good care of understanding their health and safety, and why the power companies really have to work them to failure, even though that's not necessarily the best decision in the case of wet transformers, because it makes them far more susceptible to GICs. But if they can identify which ones are the most susceptible, then perhaps they can find a mitigating solution to work around them when GICs occur. But it means that they must know what the health is of all the transformers that are in play, right, during a GIC. Okay, so again, this is back to 2010. So the major unknowns at the time were what are the solar and interplanetary events and signatures that are most geoeffective. We're learning that stuff. That's part of that is coming, right? We still can't predict them, but we're beginning to know a lot more about them. And I'll show you probably our next class. I'll show you some of the neat stuff that's going on because we're getting magnetometer networks set up so well that we're seeing how these things can impact, right? Because we have to take into effect all the local aspects of space weather impacts when we're talking about the ground level. Things are no longer a global phenomena. They are a local phenomena, local time, as well as local spatial, local in space, geography, right? What are the characteristics of extreme geomagnetic storms that pose the highest risk? We're trying to understand that, getting better geophysical models. That is always ongoing. And what is an adequate distribution of magnetometers for GIC modeling in any country? This is definitely something that we're trying to tackle, and you'll see that probably next class. In the industry side, right, so that's the academic side. In the industry side, which information, monitoring or forecasts, and on what time scale is the most useful in managing GIC risk? Scientists, this is the communication issue between scientists and industry folk, right? Is that the scientists, we study certain things. To us, magnetic field, as you saw with Austin Powers doing his little dance, that's really useful for us. But these guys, they don't care. I mean, they don't really care about magnetic field. They need to know the electric field. That's much, much more important to them. And they need to know the electric field, not in some random place or in some model, in some homogeneous thing. They need to know it at their feet, right? Under where their substation is. And they need to know it at a certain cadence, right? These are things that we've learned over the last decade. But the problem is a lot of these consortiums, they've got to be very, very quiet. They're almost like satellite vendors. They don't want to let out their secret sauce, right? So they have secret sauces, just like satellite vendors, just like McDonald's and any restaurant has. They've got their secret sauce that they don't want to let out in the open. So it's kind of difficult when we're like saying, well, we need to understand, can we put instruments inside your substation? Well, what are you doing in there? What do you need? You want to put cameras in there? And it's like, no. We need to measure the magnetic field and the electric field in the ground. Right? So there's a delicate balance between scientists and these people running these utility companies, because they've got to be able to keep their secrets and keep their own secret sauce a secret. Okay. What are the characteristics of power transformers that determine susceptibility to GICs? We talked about that. That is definitely ongoing. And then therefore determine the damage sustained under different levels of GIC, right? We've seen that power transformers are not the same, right? Dry transformers are different than wet transformers. High voltage transformers step up are different than lower voltage transformers or step down transformers. They're not all the same. And they have the different ages mean different things, right? Different latitudes mean different things. Under different bedrock, or, over different bedrock mean different things. Right? And then what are the mechanisms initiated by GICs? Still very much an active area. Some of the ways that we're learning is through the UK, for instance. They were one of the first to really say they don't care about dB by dt. They just don't care. They care more about electric field changes. The British Geological Survey holds 250,000 daily paper records of geomagnetic activity from the 1850s, but they have to digitize it. So that's a big, talk about not getting funding. Ugh, I mean, how ugly, this isn't a sexy funding thing. Who wants to fund the digitization of data? Yuck. Right? See how sometimes you don't want to, things that have to be done to look at historical events and be able to understand what's going on has to be done in a very unpleasant and unfun manner. How hard is it to get funding for stuff like this? Very, very. But the point is, after all that work, huge, huge benefits come out of it, because we can see events that are massive, right? The 1859 event in August, as well as a September 1st. How many people here knew that there were actually 3 Carrington-class events back in 1859? Probably not too many, but there were actually 3. Here's 2 of them. This is the one most people know. And I think I'll probably stop here, but this is where we are today, okay? Auntie Polkanen, a good friend of mine, and really, if you think of GICs in the United States, this is the person you think about. A scientist, the lead of heliophysics at Goddard, a really, really impressive person, has put in so much. Him and his team have put in so much, and this is a Living with a Star team. They've put in so much work for free. You know, a lot of the stuff that they do gratis. And I think that's how he got sucked in many, many, many years ago. And he realized, oh my goodness, this is insane. This is very, very important. And so he's continued that work. And to this day, Auntie is known, I think, as the godfather of GICs, if I may say that. But there's a huge, huge set of people that are working on this and have been for many, many years and making advancements slowly but surely as funding becomes available. But oftentimes, in order to make those advancements and to make the case to be able to get the funding to do this important work, they have to go and ring that Carrington event bell and say, you know, fire and brimstone if we don't do this. And sadly, that ends up being run with by the media and scaring people to put tinfoil hats on, which is really, you know, it's collateral damage. And I wish I could figure out how to make that stop. And outside of raising awareness of all this stuff, I don't know yet. It's a work in progress. But anyway, this is where I think I will stop, guys. Next time we will talk a bit more about some cool stuff, including what a reanalysis using today's SWPC modernization, through their geoelectric field grid, what it did for when we look at the 1989 event, and you can see what it looks like today, right? We saw some old analyses, but here's the new stuff. This is an operational model that you see at SWPC right now. And we'll talk a bit more about some other cool things. I'll go ahead and put this up. Whoop. Including, look at the supermag, look at Spaceship Earth re-envisioned as a real-time magnetometer ground station network. Look how much we have done, right? Even color-coded, we have so many of them, we can color-code them according to high latitude, mid latitude, and low latitude. And now that you've taken all of the courses in the second chef, you know why this is so important, right? Why we have to color-code them like this, and why that means that's so meaningful. Yeah. Even notice there's some places in the ocean, right? Oil rigs, right? Oil rigs, buoys, things like that. So we're getting there. We're getting there. We're getting there. And it becomes super important as we begin to try to do research that is more, that has scientific ideas and academic, you know, merit granted, but really has an operational bent. And we'll talk about that next time. So any questions, guys? Was this, hopefully this wasn't, I mean, we went through some dicey stuff, right? There was some stuff in there that was a bit intense. Right. I love this little plot, but you know, hopefully it wasn't completely over your heads, right? And if it is, let me know. People, especially my Patreon folk, anything that you guys didn't understand, just help me with all of it in the Patreon feed, and I will find a way. I promise, I will find a way of explaining it that is more intuitive, right? Because to me, if you don't understand it, it's not your fault; it's mine. I have not communicated it in a language or in a way that is understandable for you. This was the best yet, really, Greg? Really? You should start the next class wearing a tinfoil hat. right? The problem is that I drank with mason jars, and now I've had to get, you know, I've got a few, my moderators and VIPs have mason jars. At least I'm still working on them, but I have them autographed and I've sent them. I'm going to have a tinfoil hat, and then I'm going to have to get that, you know, monogrammed with Space Weather Woman logo on it. It's funny. People pay big money for this type of education. Oh, that's sweet, Art. Thank you. You're welcome. Yeah, well, you guys are the guinea pigs, really, for a lot of the Millersville stuff I teach. So, so you get the benefit of that. And especially those of you on Patreon who have kind of been the whole reason why I teach what I teach the way I teach it. As a matter of fact, I would not have gone into reactive power and gone into the level of detail with the transformers if it had not been for all the questions I've gotten over the course of time on Patreon. Okay, thank you. Good class. Oh, love it, love it, love it. Oh, I'm so glad. Joseph, Art, Kathy, this was great. Thanks for the work. That's Tree Spire. Thank you. Oh, good, Tim. Yeah, Tim, make sure you just catch the replay because there's a lot in here. And you're in Spokane. You've seen Aurora overhead twice. Yeah, you're going to probably get some more. It's actually been last night as well. Thank you. Understood more than I thought I would. That is the best. That's the best I could get and that's exactly what I'm trying to do. This stuff is not impossible for people to understand. It really isn't. From a conceptual level, it is possible. It's just a matter of how do we communicate it, right? It is complicated, there's no doubt, but that doesn't mean, I mean, we deal with complicated things every day, right? Any mother who has a full-time job and 6 kids and, you know, and has to do dishes and laundry, I mean, life is complicated. We have the capability of understanding this stuff. So it's not a matter of not being able to understand it, not having the mental capacity for it. We do. It's just a matter of how do we communicate it clearly. You don't understand the courses except IE. Which one do I start with? If you haven't done any of it, you start with the C courses. That's coronal mass ejections. But yes, this is an advanced course. We are now 20 plus courses into what is the space weather basics and then the advanced courses. So you start with the first chef and the C courses, and you'll see even on YouTube I talk about what the prerequisites are. So you'll see the C courses, which means C for CME, do not have any prerequisites. Those are the ones you start with because you'll learn about solar phenomena first, and then you'll move on to what I call the second chef, which is what we're talking about now. We're basically coming to the end of that. What year did that solar flare open up the ozone layer in the northern hemisphere? There's every single time we have a big solar storm, and it's really a radiation storm part of it that opens up the ozone hole. So you have to have a radiation storm, and it happens all the time, actually. 1989 did it, Carrington class event did it, 1967, 1960, or 1972. I mean, if I recall, the one in 1972 was so bad, it took 4 years for the ozone hole to close. So space weather does it all the time, but it's not the solar flare that does it. It's not the coronal mass ejection that does it. It is the radiation storm that's associated. And once again, you learn about that from the first chef when I talk about radiation storms. Okay. You got no one in particular. You got to catch up on the shows before you have good questions. Understood. Yeah, we are in advanced stuff. These topics are definitely advanced. Again, William, the C courses. You'll be your guinea pig any day. Oh, thank you, Spirit. That is so sweet. I appreciate that. Okay. Yeah, thank you, Jerry. You told him. Help a lot. Made a number of concepts fall into place. Excellent. More. Yes, next month we will probably, I think we'll be able to finish. What I might do at the end of this next course is that we'll finish the GIC stuff, and we will and then I'll make the rest of the course a free-for-all. So those who needed to catch up or those who need a little extra information, we'll just do a free-form Q&A. Help a lot. Okay, good. You are putting some love into this. Yes. Don't go. Art, come on. I've had you on for almost 3.5 hours. Gotta go. It's Halloween. My daughter wants to go to a festival, so I gotta go. Yeah, William, C course. And then what is the next in the sequence? Once you go to C, you'll notice you go to C courses, and then you'll go to, I believe the next one is F for flare. So you'll have coronal mass ejections first, then solar flares, then the radiation storms. Okay. By then you'll probably get a good feeling. If you come on Patreon, you'll get that information. I actually have a video and a walkthrough, a course walkthrough that shows you which ones to take and how. And I even have a special place that people can go to look and follow the curriculum very closely. It's a little bit easier to navigate than YouTube. YouTube is really clunky, isn't it? So come on Patreon and you can find it. Okay, let's see. Doing the dishes is complicated. Yes, I know. I know that. Oh, thank you. Thank you for the festive colors. Yes, very festive, aren't it? Thanks for this info. This is Tom. You are a great teacher. Oh, love the mini course and learning quite a bit. I'm so grateful. Thanks, you guys. I'm so glad it helped. You know, it's it can be very, very, unnerving trying to figure out what is the best way of saying it without being too flowery or too, too oversimplifying something to the point where it's wrong, where I'll get, pelted with olives by the community, operational community. And I may yet. We'll see if anybody comes at me and says, Tamitha, what in the heck were you doing? So I'll just try to make better next time. If I can buy oil paints with golds, okay. I don't know what that means, Kathy. You're funny. All right, guys. It looks like no more questions. This is great. The sun just did something. Oh my goodness. I'll take a look. I won't right now. If you can't afford the Patreon, it's still not too hard to stumble through. Yeah, you can actually, believe it or not, you can actually follow me on Patreon. I don't think you have to pay anything. So you can become a patron by just following. But yeah, I mean, my goodness, $1 a month, for goodness sake. That's all you need. Oh, you and William, you did attend my course in Dayton. That's fantastic. Well, I hope to be going back to Dayton maybe next year, if I can. We'll see. I've got some other classes and things that are lining up. I have a space weather operational school will be part of teaching in Italy for ISI. That's going to be very cool. We're going to be. I have a bunch of European colleagues that we are going to do a week of space weather operations. So it's kind of like teaching some of the Millersville stuff, but a little bit more academics bent. But we're going to be focusing it on industry partners and stuff in Europe, which I'm super, super excited about, because we've got a lot of, I've got a lot of good stuff going on here in the United States, but I really, really want to be able to open some of that up to international partners and collaborate with them. I think it's so important that we open up operational space weather and really start focusing on it and graduate new people, new scientists that have that kind of expertise, because it's just becoming too important not to. Okay, guys. I wish more professionals would approach these subjects with your passion. Oh, you're very welcome, Stinger. Thank you. That's so kind. Okay, guys. Yeah, don't invest in tinfoil. Invest in education. Yes, you can drop the tinfoil hat when you have the information. That becomes your hat, right? And that's exactly right. And you don't have to be worried about the fearmongers. So don't let any more of the fearmongers on YouTube send you off into the weeds. We have people working on it in our community, and they're fantastic people. And the industry is not just sitting there letting this happen. They are working very diligently. And you can thank the power grid, because the power grid, honestly, just by its own design, is handling GICs all the time, right? And it's handling it very, very well. It's only with the really, really big ones that it just pushes it to the point where it gets saturated and it can't, right? And that's what we have to figure out, after we try to make not happen. Okay, guys. Yes, I will, Info Dog. I am studying for my general now, so we'll see. I'm going to try to do Skywave soon. All right, guys. Thanks so much, and thanks to Jerry and Mike. I appreciate you both being moderators, and especially you, Jerry. I saw you all on a lot today. Much obliged. And anybody else, if you need answers on Patreon, post on Patreon, and I will answer you there. Okay? Take care, and thanks for dealing with all my early sound issues. Okay. Bye.